All right, let's start. All right, guys. Just a second. Okay. What are the type of machine learning that we have seen till now? So, supervised versus unsupervised versus reinforced, right? Then what else? Operational versus strategic. Yes. So strategic is something where you have to take a decision. Operational is something where you have to get some value or find the what do you say influencing parameters. Next up is regression versus classification. And sometimes we have seen that an algorithm can act both the ways, right? Parametric and non-parametric. And finally, yeah, model based versus memory based, instance based, right? So these are the five different type of classification we have found out, and many algorithms fall under either of these classifications. So we had discussed KNN and naive Bayes, right? Today, let us continue our discussion with two more versatile algorithms, which started gaining popularity these days, and one of which has been in use for a long time. One is support vector machine. Something which is relatively new, a newer algorithm. And yes, it has now started gaining its prominence in the real life applications. The other one is artificial neural networks. Something which has been in discussion in theory since the time even before computer was invented. This was under a very high theoretical applications, mathematical applications, even before the computer was invented in the first place. But people stopped using it in the late 80s because they never found the hardware which is suitable for this. But now with modern infrastructures and hardwares, again, this has got its rebirth, shall I say, in practical applications, right? Artificial neural networks. So we'll be discussing these two. One second. Just a moment. All right. Now, let's begin with SVM, the support vector machine. Now, this algorithm is one of the supervised algorithms. Supervised algorithm. So, as the features of supervised algorithm go, SVM is based on some derivative variable. we'll have to see one variable which needs to be evaluated. Depending on that, SVM works. So SVM algorithm, although it is used both for classification and regression, the support vector classifier, SVC, support vector classifier, is something more famous. In other words, SVM is more prominent when it comes to classification models. But nonetheless, it can also be used for regression models as well, without any doubt, right? Now, this support vector machine is based on a line equation. It's based on a point or a line equation or a plane or a hyperplane, which is supported by the above one is supported by a group of data points or classes, and this group is known as vectors, and the vectors which actually support, or the vectors which help in deriving the line equation, they are known as support vectors. Is that clear? Yes. Now, when we begin to learn this algorithm, when we start to learn this algorithm now, we will begin with one assumption, that our data is well classified, data is not noisy. This is one case how we will begin this with. Now, it doesn't mean that it will not work for non-noisy for noisy data. No. So data is not noisy. This is one assumption which we will begin with now. Noisy as in completely scattered. There is no proper differentiation between two classes, right? So let's say there is a class called, like in our example, let's take a y variable, a binomial y variable, right? The data points are not so much scattered or mixed. There is a clear distinction. If you draw a scatter plot, there is a clear distinction between class A and class B. This is the assumption that we will begin this entire exercise with, right? Now, please look at the first diagram here, the one which you're seeing here. This is what I have been saying. Like, so we will first see, we will first ensure that our data is well classified like this. So if I take an x and y axis, the green ones is class 1 and the red ones are class 2, the other class, right? And if you look at this line equation here, y is equals to mx plus c, that is how a line is, right? Any line, I'm not just talking about an optimal line, I'm talking about any line which is in form of y is equals to mx plus c. For example, in this example, let's say it is that line which separates this point and this point. Yes. Now, if any unseen point comes into picture, unseen as in from your test data, let's say this point here is coming from your test data. If it is on this side of the line, it gets classified as a red class. And if this unknown point is in this side of the line, the machine will classify it as the green side, the green class. This is how support vector machine works. So by now you would have guessed one thing. In running support vector machine algorithm, what is more important? It's more important for us to come up with this line, right? So there would be many iterations that the algorithm will be doing in itself, and based on these iterations, it will come up with a plane or a line or a point which exactly separates both of these data points. Is that clear? Yes. Now, the ultimate question at this moment would be, is it that simple? I guess not. There are a few things which we have to take care of it. So a few things which we have to know so that we can set our tuning parameters, and the algorithm will automatically decide on the best line that can separate both the classes. Is that clear? Now, again, in this example, I am primarily going with a classification model with an assumption like you're seeing in my pick that the data points are well separated. Data points are not mixed. Do you see any red points over here? Do you see any green points on this side of the line? No. This is how I'll assume and go forward with. Clear? Now that doesn't mean that when the algorithm itself is starting, algorithm doesn't assume this. Just for our learning purpose, this is my first assumption that I'm doing. This is not an assumption of SVM. Please do not mix it. Like we have one assumption in linear regression where my y variable has to be normal. So that is a proper statistical assumption. Here, the assumption that we are taking is just for our learning purpose. That's it. Because we will begin with one class of support vector machine called linear support vector machine. We will understand entire mechanism of support vector machine using that example, and then we can see how we can modify that. Clear? All right. How many variables has it? So usually, like we have one, we should be having one y variable, right? So I'm explaining, and we will also be explaining the SVM algorithm when we are implementing it based on my y variable. It will be always based on the y variable. Now, yes, sir. So it works for everything. So as of now, just for simplicity's sake, I'm taking a binomial classifier. It works for multinomial data as well, right? All right. Now, the goal of support vector machine is to find the optimal separating hyperplane. That's it. So like I said, I need to find this line. Even if data is like this, even if the data is mixed, even if the data is multinomial, I have to find a line like this. You know that lines can be infinite, right? But there has to be one line which will separate everything, right? Let's see. So I have two classes here, as you can see, men and women. Men represented with blue plus and women with 0 circles, pink circles, right? All right. So my goal is I have height in centimeter and weight in kilograms, and I have certain weights and heights for men and women. So 3 variables: heights, weights, and gender. Now let's say I'm getting my test data or unseen data where I only have weight and height. I'll have to predict if that weight and height belongs to a man or a woman, right? So as you can see on the lower end, as in like lower heights and lower weights, you have got a lot of women concentrated over here, and on the higher end you have men over here, right? Now this is how the data is. So as you can see in this pic here, I was able to draw one line that is separating both the classes. Yes, one line that is separating both the classes. Now you must be wondering why I am using the word hyperplane always. Why don't I stick to using the word line? Why do I keep jumping around calling it as a line, plane? So fact of the matter is, the line that you're seeing here, or the one which I have shown before, this is perfectly existing on a two-dimensional plane, right? It's a two-dimensional data, and yes, I mean two-dimensional as in I have x and y. Yes, this line can exist, y is equals to mx plus c. But what if your data is one-dimensional like this? So there can't exist a line. I mean, like there will be a point now in this case. But what if your data is three-dimensional? I have x, y, z axis. So three-dimensional spaces is not made up of lines. I have xy plane, I have yz plane, and I have zx plane. So like that. So those are the three basis planes. So those are the planes based on which the entire graph system exists, the 3D graph system exists. And we also know that a three-dimensional data is a collection of infinite number of planes. So when your data becomes three-dimensional, I'll be not using the word point or line, I'll be using the word plane. Now, are we restricted to only 3 dimensions? We have multi-dimensional data as well, right? Hashtag interstellar. Yeah. So, no, just kidding. Don't get that here. So in our n-dimensional data, we will be using the word hyperplane because none of these 3-dimensional definitions is applicable for a multi-dimensional data sets. Right now, like why I said interstellar, like they had used 5 dimensions there. If you had seen the movie Tesseract in the end, so you can't find one plane which is defining, let's say, a time moment. So your 4th dimension there is time. When you can see that the protagonist can see a lot of pics, lot of events from his daughter's bedroom, right? So 5th dimension being gravity over there, right, which can transcend through any planes. So can we use the word plane in that case? We can't, right? So hence we'll be using the word hyperplane. And this is really important because when I begin with one small assumption saying that my data is distributed across 2D and data is properly separable, data is not mixed. Eventually we'll see what will happen if data is not mixed. We might have to convert our data into a higher dimension. That is what this entire SVM is all about, right? Okay, let's come back to this discussion. You see these 2 pics over here. So like I said, there can be one line which can separate the entire data very well. Also, I can have infinite number of lines which do the same thing. So within this gap and this gap, you can have a lot of lines that can come in, right? Which one is the best line? That is what we have to determine. Now look at the next 2 set of examples. When I say which one is the best line, I think this picture should give a small idea on how we are able to fix it. As you observe carefully here onto the green line, yes, this is separating the data. But what if this data point, which is too close to it, let's say a new data which has come up, let's say let's put that in this color, a new data point that has come up, let's say it's over here, but when in actuality it should belong to this class here. So this data point gets misclassified, right, because of the closeness of the points to the separating hyperplane. Yes. Whereas on the other hand, look at this one, the distance d from the nearest point to the existing line. So this point, I'm assuming it to be the nearest point here. So if this is the nearest point, the distance from this point to this line is huge. Yes, as compared to the same point on this graph here, this one here, the gap between that nearest point and the line is little bit lesser, right? Now, look at the second case, the optimal case. When your distance between the point and the line is little bit far enough, the d is little bit far enough, you are having a proper classifier here, right? There is no error of having a misclassified data. Yes or no? So hence, this is the reason I said the entire goal of support vector machine is to find a line which is a little bit far away from your nearest data point, right? Now, as usual, like if you remember when I was talking about point estimators and interval estimators during our sampling lessons, if there is an election coming up and if you're going out with an exit poll, you will never say that XYZ party will win exactly 130 seats or 140 seats. You'll never say that, right? You will say, you will give one confidence interval, right? You will be giving one margin, or let's in very layman's term, let's call it as an error. Yes. So you'll say, hey, this will win 120 seats plus or minus 10% error, or plus or minus 5% error. I hope you're able to understand what I'm saying, right? So likewise, in support vector machine, a simple line, I mean, like in this case, when we are drawing a line, a simple line is not enough. You will have to define a margin. Clear? So here comes the concept of margin. And you see, a support vector plane, a support vector hyperplane is decided by the distance of hyperplane to the closest data point. And this distance has to be high, right? Now, take this point here. Please look at this one, this particular graph here. Take this point here. Let's assume that this is the closest point to the line which we have decided. Yes. Now first calculate the distance d between the line and the assumed closest point. Let's say the distance is d1, right? So I can draw a line passing through the point d1. Yes. Now that being said, if I can just double this distance. Yes, please. So if I can add one more d2 here, which is equal to d1, which is just double of it. So look at the total length d. This total length d. This is your margin distance. Instead of depending on one line equation, now you are depending on a range of equation, a margin, right? So if you have not got the perspective, I'll just explain it to you once again. Please listen it. So here is the linear classifier that we have begun with. Just to repeat whatever we have said. So we with a line equation like this, wx plus b or mx plus. Okay. So just to avoid this infinite line problems, we will be fixing on one particular line. But let's say if you're fixing on one particular line, this is the problem that we would be facing. So if you are looking at this line equation here, here. So if I'm considering this line marked as cross, so this line will give me some or the other misclassification error. It's already giving it. But whereas this line is classifying it properly. Now, for one small training data, you can't determine this, right? If you are just going with the mx plus c kind of a line equation. So to avoid that, let's create a margin. Now, once we have created a margin, so you have understood like why I have created a margin. Distance from nearest point, double the distance from the line to the nearest point. So I'm creating a margin. Now, this is one type of margin as you're seeing here. The black color line is my actual line and the yellow zone is the margin, right? So within that margin, let's say if there is any point which falls under that margin, you see, again, let me explain it to you in this perspective of a misclassifying line. So here, if I come up with a margin like this, so margin number 1 and margin number 2, right? Now look at this. Look at this zone of data points here. This one, this particular one, which I'm encircling. Yes. And now look at this zone, this entire bunch of it. Don't you think this is now a proper classification of the data? Yes. Plus, we will be ignoring all the data points which is falling under this margin. So once you ignore all the data points which is falling under this margin, so a bigger line gives a bigger separation, right? It gives a proper separation, right? As you can observe here in the screen, every one of you.
It is not a line, actually, it is a space.
So you can call it as a line plus or minus distance. So this is what I'm saying. So if this is a line, this is D and this is also D, right? So I'm now having two line equations again for the two more line equations. So as you can see, this entire margin is now properly classifying the data, right? Right? Margin is properly classifying the data, plus the one of the features of margin is I'm just ignoring all the points which are falling under this margin. Now my classification is proper. Yes. So just put this picture into your mind. Let's move to the next slide and see how the margin actually is dividing. Now look at this. First of all, if I have a smaller margin, a very small margin, this also doesn't solve my purpose. A smaller margin is as good as having one single line. Yes, but now look at this. So should there be any data points within this zone? Should there be any data points within this zone? This will not be considered for classification. Clear or not? And there is a colloquial term for that. They call this as a no man's land. Any data point present in this particular zone is not classified at all. It's ignored. But look at the rest of the points here, here and here. Both are now properly separated, right? This is the concept of support vector machine. And if you closely observe, look at the black line again and look at its nearest points. This is point number 1. Let's call it as distance D1. And let's say on the other class, green side, let's say this is point D2. This is the distance D2, right? So either I can take 2 times the distance of D1 or maybe like 2 times of distance D2, whatever or whichever is convenient. But nonetheless, this entire black line, the middle line, is supported by the data points, right? It is supported by the distance between the data points, right? So hence the name support vector machine. And these data points which are defining the black line equation, these are known as support vectors. They are those data points that the margin pushes up against. So the margin is just touching these points, right? Yes or no? The margin can't go beyond these support points. And there can be a lot of other data points which can fall under this margin, which will be happily ignored. Clear? And this entire SVM mechanism is known as maximum margin linear classifier. Linear because I have a line equation which is classifying my data. Margin because I'm not taking one single line, I'm taking a margin. Maximum margin because my entire target is to maximize this margin. Maximize this margin so that my data points are properly segregated. Right? Again, if you have any doubts in why maximizing the margin, let's go back to this pic and see. Yes, let's take this for instance. So you see the data points are just touching this, right? So this can't be a proper support line because the nearest data point here where my mouse pointer is, the distance is very negligible, right? So this leads to misclassification. Yes or no? Misclassification because there would be some amount of bias if I'm doing this kind of a thing. Now what I'll do is let me move on to the next nearest point. Is this the next nearest point? Yes, this is. You can see my mouse pointer here. This is my next nearest point, point number 1, or this point here. This can also be my next nearest point. Now, if I try to draw a margin based on either this or this point, still the line will be very small, right? Still my misclassification problem exists. I have not completely solved it. Now again, let's go for another iteration where we find the next closest point. Let's say after many iterations, we come up with one fact that this point here forms an optimal distance point. So what I'll do is I will draw a line which is just passing through that parallel to this with the distance D. Okay, 1 second. Clear? And so the distance d, what I mean by distance d is distance from this point to the black line, not the margin line. Right? That is my distance d. Now, if I'm taking this distance d, I'll add up one more distance of the same length d over here. I'll just double it. So if I'm doubling it, then I can also have one more line passing through this point here, passing through that particular zone here. Yes. Now, once I do that, now closely observe points which are on this end. Points which are on this end versus points which are on the other end over here. Now, aren't they properly classified? Because I'm bluntly ignoring all the intermediate data points over here. Yes? Clear? All of you? So this is the entire goal of support vectors.
The distance will be higher between the
Margin and the classification point, which is the, which one are you talking about?
like the black line and the classification line.
No, this is not classification. This is a margin. You have to consider this entire thick line as your classification line. You are not considering just this middle line as your classification line. This entire range is now considered as one single thick line. Right? Instead of having one thin, I mean, like just in layman's terms, instead of having one thin line, you have one thick line. That thick line is also diminishing some of the data points. Right? Clear with this? All right.
So how do we decide the margin?
So the margin length is decided by the distance of the nearest point. So how did I begin this with, guys? I had begun with considering this as my most nearest point to my line over here. So let's say I'll first decide on one line, like let's say I'm deciding on this line here, y is equals to mx plus c. From this line, I'll start iterating, and I will find the point which is closest. So if the distance between that line and point is very small, I'll keep going for the next iteration till I get some optimal distance. So here, let's say this point is the point where I found my optimal distance. Yeah, I'll come to that. I'll come to that. So see, at the end of the day, I should not swallow many points in the no man's land. That is one restriction which I have to keep in mind. More the number of points coming under no man's land, which means we are losing a lot of data, right? We are losing a lot of data points. Yes or no? So this is how this optimal distance is calculated by the algorithm itself through iterations. Now, once we find this distance, we will draw one line that will be my margin number 1. Again, I'll come back to this middle line. I'll take one more equivalent distance d, and I'll draw one more line passing through an imaginary point over here, right? It doesn't necessarily mean that it should pass through this point. This point is just a coincidence. That's it. There can be any point from one class, and it should be double of d, double of the distance where you have first decided your nearest point. Is that clear? Now, if you look at this very thick line, this thick line has now separated this reds and greens, right? All of you. So now if I'm taking any unseen data, if that unseen data is lying somewhere over here, I can confidently say that it belongs to this class plus 1. This one here, this green point belongs to this class. Should the data point be lying distinctly over here, so this belongs to the other class. That is how I would decide. Now, coming back to her question, how do we truly decide that this is one single plane? So for that, please look at this equation over here. See, look at it. Like I have said again and again, we are maximizing the distance. So maximizing the margin is good according to our intuition, like how I have found it out. But then I might lose some data, right? So that being said, this entire system empirically works well. Despite the fact that I am losing some data, I have one conclusion from various tests and various researches which say this kind of a mechanism empirically works very well. This has been tested, and despite the fact that you're increasing the margin, it is working very well. Now you might ask again and again, like, we are including a lot of data points in the no man's land if you are increasing the margin. Now here you have to remember one thing: the entire equation depends on just the support vectors. Other data points can be happily ignored. Once I decide on my support vectors, it's okay if I don't have any other data points. These support vectors alone can help us determine the class of an unseen data. This is what is the principle of support vector machine. Again and again, I mean, like, how do we verify this? How do we prove this? Yes, there can be a lot of mathematical equation. We can write a lot of vector equations and prove it. At the end of the day, it has been empirically proven that yes, this works well. Is that clear to all? So if you are still feeling that we are putting a lot of data in the no man's land, you don't have to worry about it, because the entire system works upon support vectors. So just having the support vectors is more than enough. So all you have to do is find that point which is farthest from the line that you have decided, right? Or if that sentence is confusing, let's stick to a simpler sentence. Find a margin which is wide enough, right? Maximum margin. Now let's look at this. Why did I say maximum margin? Now look at pick A and pick B. The one on the left side, it is also a margin based separator. On the right hand side also you have a margin based separator. Now when you have this kind of a situation, still my misclassification problem is not addressed. My misclassification problem is still not addressed. So distance between this point and this, or maybe like consider D1 here, or consider this distance. If I can consider this blue point to be the nearest point, so let's consider this as D1, whichever is convenient, just for the example's sake. Now this line is not the farthest line, right? This distance is not the farthest. In my next iteration, I can come up with this distance over here. I can come up with this distance over here. Or maybe like from this line, this can also be one with the maximum distance, right? So hence, look at this scenario now, how the algorithm has decided on a line equation y2 instead of choosing a line equation y1. Please look at this. Here, this distance m, or in our old notations, how I used to call it as d1, this distance is the maximum, right? So if I have a maximum distance, as you can clearly see, two classes are classified very properly. Yes, I am ignoring a lot of data points, the one which I'm crossing over, like this data point will be ignored, this data point will be ignored, a lot of data points got ignored. But I don't have to care about it, because the entire equation depends on the support vectors. Is that clear to all? Now, again, one more pick to explain why large margin is important. Look at this line equation here. This line equation, no doubt, separates the points properly, but you know that there is a phenomenon called overfitting. So this kind of a situation definitely leads to overfitting, because here is a place where you can find maximum variance between 2 points, right? So between this class and this class, you do have maximum variance, but maximum variance will lead to overfitting. This might work well on your training data, or maybe on one test data it might work well, but you keep increasing your test data or you keep changing your test data, it will not give the same accuracy. It will work well on your training, will not work well on your various testing samples. Clear? So this is not a proper, although if you're looking at the intuition, this might look as if a proper separator between two classes, right? But look at the below line here. Yes, I'm compromising on this blue point over here, right? Yes, I'm doing one tiny level of misclassification in this example, but that's okay because I have an optimal variance. Yes, so I'm reducing the possibility of overfitting. Now I should make sure that this misclassification error doesn't increase. So now how does this line equation depend on? The line equation depends on your misclassification error. Get a line first which gives you the least misclassification error. That's it. So line number 2 here in pick number 2 in the below gives me the least misclassification. So let me first consider that. And let me try drawing margins. Now if this margin is coming up with the proper separation between class A and class B, even if I'm ignoring few points or many points, I'm ending up with the proper support vectors, then I'm happy with my entire algorithm. Empirically, if I can give a new unseen data or a new test data, this algorithm will work well in case 2. Is that clear to all? Yes? All of you? Okay. Now, what happens if you are allowing a lot of points to be misclassified? We will be having underfitting. Your training itself will not work properly, right? You'll not have good accuracy in your training. That's an underfitting, isn't it? So make sure that your misclassification is not high. Also make sure that your variance is not too high, right? Just a second. Now come to the next example. In my all previous cases, I have seen that my data is properly separated. Here the data is mixed. You can see some of the solid circles mixing up with the normal circles and vice versa. What to do with this case? What happens if I come up with a linear line like in my previous case? So if I come up with a line equation like this, this might lead to two things. One, either I'm going for an overfitting problem, or two, I'll have high misclassifications. Yes or no? Look at this. I've got 1, 2, 3 data points which are clearly misclassified. So this line is not proper. I can't come up with a line, right? Or if I come up with a arbitrary shape like this. Remember, like when we were discussing linear regression, we were fixed to only one line called y is equals to mx plus c. We can come up with a curve as well by connecting all the points here. Like if you wanted to minimize the distance, just instead of drawing one straight line, draw a curve, draw a polygon. But that leads to overfitting, right? Yeah, variance becomes very high. So that exactly that case will happen if you are getting into this kind of a curve equation. Let's say you come up with a curve f of x, which will properly classify everything, but this will lead to overfitting. This line here will lead to underfitting because there are a lot of misclassification error over here. What do you do in this case? Here are the three things, like two things I have told you. Let's look at the third thing, what we can do here. So two things, as in, again, I repeat, if your data is noisy, then let's say you're coming up with a non-linear boundary. Non-linear boundary as in the kind of a weird shape that you're saying. It's a non-linear boundary, right? This is what first thing comes to your mind. If the line cannot separate, if the line gives you a lot of misclassification error, come up with an alternative f of x. That is one option. Or bluntly depend on a linear boundary that can classify with maximum accuracy, right? Both the things have a problem. If I'm having a linear boundary with maximum accuracy, I'll go with bias. There will be some biasing involved in this, which will finally lead to underfitting problem, right? This will not work well in the test training data itself. Forget about test data. If I'm having a non-linear boundary, I'll have high variance, which will lead to overfitting, right? So in case if your data is noisy and if you're coming with a non-linear boundary, that's known as a hard margin. The one you're seeing here is actually a hard margin. Now, should you come up with a forcible line equation here, like this, just to separate out these points, let's say you're coming up with a line equation here. This is known as a soft boundary, right? Both of which are not so helpful. What should we do in this case now? Let's get back to, let's say, linear regression, for example. Your assumption is y should be normally distributed. That's my first assumption, right? Come to logistic, come to GLM models now. In GLM model, does this first assumption hold true? It does hold true. Although your data might not be satisfying it, but still, even in GLM, y should be normally distributed. But your actual data is not normally distributed. Let's say if you're trying to do a binomial classification, your data is following which distribution? It is following a binomial distribution, right? So what do we do in this case? We had transformed it. We did a logit. Yes, p by 1 minus p. We did some transformation, right? So that, yeah, we applied some transformation by which we were, at the end of the day, we were able to apply logit is equals to beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. And finally, we came up with an equation y is equals to exponential of, yes, divided by 1 plus exponential of beta x. Yes. So that is what we are going to do here. We will not change any of these data points. Rather, we will transform these axes. So x and y can become x square and y square. That can be one possibility. Yes. Or for example, if you have a single line, if you have a linear data like this, the one which you're seeing here on the screen that I had shown you first, if I have a linear data like this, then I'll transform this to x and consequent x square like this. If I'm transferring this into x and x square, now I'm having one more dimension here in this case. Now, when I say transforming, I'm transforming all the points, right? So the points which were rather linear in my previous case, now they would become distributed in this axis. Look at this. Now I'll have new points here, right? Just a second. So I would definitely end up having newer points over here, right? If I'm drawing an equation between x and x square, yes. Now, if you have this a two-dimensional data, on a two-dimensional data, you can easily draw a line, yes, or maybe come up with the maximum margin effect. That can be one possibility. Alternatively, let's say in a two-dimensional axis, if you're not able to find an optimal plane, if your data is noisy, convert that two-dimensional data into three-dimensional data or into some higher dimensional data. Then you might come up with a plane which will be a proper hyperplane that is separating my data points, right? So this is what we are going to do here in the next phase. And that mechanism is known as kernel trick. The process in which you are transforming your data into a higher dimension, that is known as kernel trick. Just a second, let me show it. Right? So if the data is not linearly separable, increase the dimensional space. You will now have something called kernel trick. Clear? And a kernel is nothing but a mathematical transformation which uses a certain function. And this transformation transforms the data into a new dimensional space. This entirely transforms the data into a new dimension. That is what is meant by kernel. And once you transform this into a higher dimension, now here is a small assumption that should you transform this into some higher dimension, yes, the data might become linearly separable, right? Let's say from 2-dimensional I made it 3-dimensional data, then I might come up with a plane which is a proper separation plane. Or maybe if I'm going for a n-dimensional data, I might come up with a hyperplane equation which is properly separating my data here. Yes, I hope you have understood the concept. And this kernel function, or the function that you use in a kernel, that function is known as a basis function. See, why do we have to depend on mathematical equations at this phase? Because you see, if I'm bluntly depending on intuition and iterations, that becomes more and more costly with regards to the processing powers. So come up with a mathematical equation that might solve half of my problem that I will face with my hardware. So hence this equation or a function that can be used in the kernel, and that function is known as a basis function. Clear? So if you have a clear linear separator or linear line, so you don't have to do anything, x becomes x stays like x, your equation will be ax plus b as usual. But should you go for a polynomial basis function, your equation now changes to ax plus b whole power n. So if x and y is not solving your purpose, go for x square and y square. Yes? Or if polynomial is not working, you can go for a Gaussian basis function, which can be this equation over here, 1 by exponential of 1 by f of x. This is the simplest form of a Gaussian radial equation. Clear? You also have sigmoid. Sigmoid is nothing but exponential of f of x, exponential of f of x divided by 1 plus exponential of f of x. We are familiar with this equation, right? So you can come up with any of these basis functions, just like how you did log transform, square, square root, cube root, in your pursuit to convert your distribution of y to a normal distribution, to have a proper dimensional and a proper hyperplane that can separate the two classes. I can come up with a kernel transformation using a basis function. And this basis function can be linear, polynomial, Gaussian, and sigmoid. In terms of Python implementation, we'll be basically focusing on these 4 or 5 algorithms. There can be many number of algorithms depending on the kind of data that you have, but we are not getting into that kind of a complexity. Clear? Chances are most of my problems can be solved within these 4 kernel basis functions. Yes? So I hope you have understood the entire picture, right? When I began this class with the data which is not so noisy. I have a clear distinction. The data is not mixed. I have a clear distinction between x and y. Sorry, class 1 and class 2. Then I was able to come up with a margin. But when my data became noisy, I had 2 options: stick to the margin or draw a curve. If I'm sticking to the margin, I'm having underfitting because I have a lot of bias. If I'm getting into an arbitrary f of x, a hyperbola, parabola, ellipse, or something, then I'm okay. Okay, let me just explain that with even more simpler example. Just a second. Oh yes. If my data is proper and I'm coming up with a line, yes, that's a proper separator, end of the story. If my data is noisy, still if I'm coming up with a line. So let's say here in this case, if I come up with a line somewhere over here, 1 second. So if I'm coming up with a line over here, problem is there is a lot of misclassification happening, right? So left side of the line, no doubt I have read, but on the right hand side of the line, I have 3 data points which are getting misclassified. So that's not solving my purpose. Or let's say in case of a hard margin, let's say I come up with this kind of a hard margin where all the reds are on one side and all the blues are inside that rectangle. That's a hard margin. Can I not get a rectangle equation? Yes, I can get a rectangle equation, and I'll call this rectangle as my separator hyperplane or separator line or separator margin or hard margin. So what is the problem with this hard margin? Bias. Yes or no? So what did I do? I transformed this into x versus x square. If I transform my entire data into x and x square, see my points have also shifted now, right? Now if the points are shifted, now look at this. There is a high possibility that I can come up with a margin which I had explained to you before, which you can see in this pic here. This is what I was explaining. This is what I was talking about. Is that clear? All of you? All right. So what should be the tuning parameters for your support vector machine? One is your basis function. Which function you should be choosing so that your data is properly transformed into a higher dimensional data. So if it is a polynomial, go for the n value, or if your data is mostly containing classes, go for a sigmoid. If you're working on a regression problem, go for a Gaussian or a radial transform function, and so on. It all depends on which data you're working on. Yes, that's my first tuning parameter. Second one is learning rate. Learning rate as in how many iterations should I go for? And once you are going with the iterations, I'll come up with a lot of features, right? Like one is like misclassification error, which should be minimum, or maybe variance, which should be optimal. Yes, so these are your learning rates. This can also be one of your tuning parameter. Clear? There is one more tuning parameter called C. I'm not getting into that complexity now again. C is almost equal to learning rate, but it has its own significance. I'm not getting into that explanation now. But I hope you have understood these two parameters, right? How do I tune this model? Yes, all of you? Which one? So the tuning parameters would be, first of all, the basis function. Which function you should be using. And the second tuning parameter is the learning rate. Right? Or number of iterations. It can be number of iterations. Because you see this entire thing is working on based on iterations, right? So your learning rate can be your iterations. Your learning rate can be other metrics which it is calculating during the learning, and so on. So learning rate would be a percentage. It could be expressed as a decimal number, right? Okay. What are the applications of support vector machine? Where it is used mostly. So guys, one more thing. I'm so sorry. Just to explain the kernel functions again, just to have a proper closure to your basis functions. Please look at this example. If my data is two-dimensional here, as you can see in this case, but data is very noisy. So here, instead of coming up with a line or instead of coming up with a soft margin like this or a hard margin like the circle, I have used a function phi of x, and this phi of x is transforming my entire data into a three-dimensional plane. Now, once your entire data has been transformed into three-dimensional plane, now just imagine this plane over here. The points below this plane are properly red. The points above this plane are properly blue. That forms a proper line of control. Yes. So if you have this, an unseen data will be easily classified, right? This is what is the meaning of kernel functions. So if you want to look at the applications of SVM, of course, yes, classification is the biggest application of support vector machine. One of the most used way is going for image processing. Image processing extensively uses support vector machines. Handwriting recognition, that's also one of the areas where support vector machine has been used. So there is one classical example that I can find on internet every time I look for, in every Coursera video or any kind of YouTube video. There are a set of dogs and cats. There can be a possibility that a cat, I mean, like dogs and cats both have separate features, right? Right? Dogs can grow a little bit big. Cats, on the other hand, they are a little bit smaller. Let's say we have taken a breed of dog which is very small, fluffy, and it is like groomed like a cat. I mean, like the owners like just groomed it like a cat, and vice versa. Take a cat which is a little bit hefty and a little bit big enough, and it is completely groomed like a dog. With the machine, I mean, like it would be slightly difficult for a human with the naked eye to identify instantly whether it is a cat or dog. You might mistake you might mistake a cat for a dog, right? If the grooming is not done properly. This is I mean, like, so that is the case where SVM clearly helps, and they have actually taken, I mean, like in Kaggle, I have found a proper data set which can do that actually, which can properly separate these two. Also, one more example that I keep getting is there would be pics of George Bush senior, George Bush Jr., and Bill Clinton. So all the three are famous for giving a same type of an expression in their pics. So George Bush, both junior and senior, they're related, of course. Their features would look similar, and then there was Bill Clinton in between these two people, and who also had same kind of mannerisms. So there were pics which were classifying, like for example, like let's say Mr. Clinton's pics as Bush. There is that is a point where you had to use a properly tuned SVM, which could clearly classify between these two gentlemen, these three gentlemen. That is also one classical example that you can find with SVM. Now, do we really use SVM in all image processing cases? No. That is where another set of algorithm kicks in, which is known as convolutional neural networks. CNN. That is also a substitute for SVM when it comes to image processing. Right? Because I have worked on one document recognition algorithm where I had to extract tables from financial reports. In financial reports, you will have a lot of text plus the tables. And also my problem is the tables need not necessarily occupy the same space in my PDF document. I can have a smaller tables, like let's say just divide this document into 2 columns. I can have one table which is limited to only one of those columns, or I can have a full length table. Yes, and sometimes my table can be spread across 5 pages, right? And sometimes within this table, within one single table, I can have a break in the table and have some text, and again another table starts. Not again the other part of the table starts. So I'll not be able to identify it properly, right? Unless I have something called OCR, optical character reader. I'll have some manually placed data points. The machine has to learn, and it should try to separate between text and tables, right? So there are some parameters which are classified as text. There are some parameters which are classified as table boundaries. I need to separate these two classes. So I had tested it on both the algorithms, SVMs and ANNs. Both work well. So that's the reason why I have put these two together, just because of their application areas. Is that clear to all how SVM has worked? The basis behind SVM. So 2 things you have to remember. One is the maximum margin algorithm. The second is kernel basis function. These are the 2 words which keep revolving around SVM algorithm, right? Even in terms of the implementation purpose, implementation perspective. Clear? All right. Just tell me one thing. I mean, like in all these discussions, like just one general knowledge question. Which is that one organ, or what are those 2 organs in your body which doesn't stop? If it stops, that's a disaster. Heart and lungs, brain. If lung stops, I can have an artificial lung. Yeah. I can have a pumping machine installed inside of me which can act as a lung. That doesn't mean that you can smoke as much as you want.
Ventilators actually.
Yeah, ventilators actually do like that. I mean, like they cut the throat over here and they insert a pipe. So that's when your lung starts pumping. So no, you're right when you said heart, and even heart can be replaced. Heart can be replaced. Heart transplantations. Liver can also be replaced. I can cut half of your liver, put inside my. That is like if our blood groups are same, you're O positive, right? Very good.
Actually, liver regenerates.
Liver regenerates. So if I cut a half of you, I remove my entire liver, put your liver. After like an year, I'll have a full liver. You will have your full liver. Yeah. Like Liz. Liver is the one which grows fast, and that's also a problem for it. Like if should there be a cirrhosis, the death tissue grows and liver is gone. Rest in peace. Now, brain and heart, even heart can be replaced. Yes, a lot of heartless people around here. Brain, why am I specifically targeting on brain? Let's see after the break. Yeah, let's take a break and let's see what brain is all about. Right? We'll have a. Guys, if you can just go through this document here, I have given you a list of kernel functions. If you just feel that kernel functions are limited to those 4 I have discussed, no, those 4 are the basic used or mostly used kernel functions or basis functions. You can have many. So I have given you the example of polynomial Gaussian sigmoid. When can you use a linear kernel? I mean, no kernel at all. When can you use no kernel? So when you have a properly segregated data, no noisy data, right? So you already have your high dimensional features. So you don't have to go for a kernel. Yes. Gaussian kernel. See, we have seen that if your data points are large enough, like during our stats class, we have seen if your data points are large enough, that can lead us to a normal distribution, right? So that's the reason why we take sample size greater than 30. If it is less than 30, that might end up in T distribution or some other distribution. If your data points are huge enough, we might come up with a Gaussian distribution, a normal distribution. So Gaussian kernel can be used when you have a low dimensional data, as in 1 or 2 dimensions, right? But your data points is huge number of data points. So this is the case when there can be a lot of scattering, a lot of noise. Yes or no? When there is a noise, you have to come up with a kernel, right? Clear? So that's when you come up with a Gaussian kernel, right? And sigmoid kernel, when you come up with that, same, large enough data, but your variable is your dependent variable is binomial or multinomial, right? You can't come up with a normal curve when you have a categorical variable, do you? No, right? That is when you have to come up with a sigmoid. So you have other kernels like polynomial, string, chi-squared, histogram. Will not get into all those, not required. Knowing these 4 basic kernels is more than enough. Now, if you're doing any kind of advanced research on SVM, or maybe like if you have worked in and out on SVM, or like if you're like let's say a big project is depending on SVM, maybe you have to get into those things. Also, all these kernels are mathematically derived, including the margins. There is a proper mathematical derivation for this margin. Again, we don't have to get into that complexity. I have although included the derivation here, we don't have to get into that complexity. Just we have to understand that we have to maximize the margin. That's how we will be changing our tuning parameters. Clear? That's about it. All right. These are also some of the cases like just to decide which kind of a kernel basis function you should be depending on. So typical cases like let's say if you are looking at a text classification problem. Text classification, like we had done a naive Bayes classifier on the Twitter data yesterday, right? So what did we have in our data sets? We had a feature vector and we had a sentiment, right? Some words leading us to positive sentiment, some words leading us to negative sentiments. We had got 2 data points over here. We had used naive Bayes. We can also use the same SVM for that kind of a classification. Yes, and if you look at that file carefully, I have also included a code for SVM. If you can look at the yesterday's file, I have included a code for SVM as well. How to do classification using SVM. So if I'm doing a text classification, I'll be fixing to a linear SVM, LSVM. I don't have to convert the data. It is already into a higher dimensional data. There will not be any kind of noise. That is what is empirically proven. But only thing is, your training set should be a little bit smaller. Your training data set should be a little bit smaller. So yesterday I had taken like 16,000 records. So I have many data points, 16,000 records or 16,000 tweets, which means I'll have many words, right? Many terms, right? So if my data size is increasing, I might have to reconsider. But if my training sample is small enough, I can go for a linear SVM, right? But if your data is intermediate, I mean like not too large, but yes, mediumly large, you can go for a Gaussian curler. Is that clear?
Which is preferred.
No, that's what I'm saying. I'm giving you an example of text classification where your data is small. If your data is small, you can clearly fix with linear SVM. Your data is intermediately large, like 10,000 records, let's say. You can go for a Gaussian, but if it is exceeding that, SVM can be slow with Gaussian. You might have to either add more features or use the logistic regression model, logistic regression of SVM with a linear kernel. So that increases the complexity of SVM. Maybe you will not choose SVM at all. Maybe you will depend on either naive Bayes or maybe you can go for any other algorithm, artificial neural networks or something else. Part of the reason why when I had built a chatbot, when we had built a chatbot, we didn't rely on SVM much. We knew this is going to be a problem when it comes to larger data sets. Because in a chatbot, my data is ever increasing. My data is highly dynamic. So we expected SVM might create a problem. So we went on with the recursive neural networks. It's a different story altogether. Clear with this? All right. Let's go for a break now. It's 10:40. Let's come back. Now, if I look at all the algorithms till now, we had, one sec. So all the algorithms till now, it had some, like some equation parameters, etc. That can be one class of algorithms, or some algorithms which has some algorithmic steps and calculations. Like for example, you have seen KNN. It follows a certain algorithm, K nearest neighbors, or it can have both equation plus iterations, yes. Now based on all these things, you had supervised, unsupervised, or reinforced. We are about to discuss a model which by default is semi-supervised, but it can act like a supervised. It can have a version where it is a supervised algorithm. It can have a version where it is unsupervised algorithm. It can also have a version where it is reinforced algorithm. And that class of algorithm is artificial neural networks, right? So our discussion on artificial neural networks begins with neurons of human brain. So the very first motivation towards artificial neural networks way back, like I've told you, right, like ANN has been there in this world much before computers were invented. So people were always curious enough just to try out any method to transform human intelligence into a machine, or maybe like just try to mimic how a human brain works, right? So can we really mimic? Can we really mimic how human brain works? Apparently, yes. This is what people have told, and this is what people have found out. If you please look at this. So our brain consists of two major parts, cerebrum and cerebellum, like what you call a small brain, big brain, and so on. One part of which is responsible for actions, the other part which is responsible for memory, and so on. Right? Now, that being said, if you can look at the different divisions of our brain, I have this optical lobe, which is responsible for your vision. God forbid if anybody's optical lobe has a kind of a clot or has a kind of a infection or an injury, they'll not be able to perceive images properly. Or should there be any damage, that's what causes various health conditions like color blindness, yes, or even retina, and to even some extent eyesight. Although eyesight is mostly dependent on retina, but if you look at higher sites, like people, I mean, like I used to have a friend who used to wear glasses of power -12. That doesn't have to do just with the retina. Like even if you do a LASIK, that might not solve this issue because it has to do with your optical lobe. Temporal lobe, on the other hand, temporal lobe is something which is responsible for your long-term memory. How do you still remember to write? How do you remember your mother tongue? Like, let's say, for example, I have stayed in many parts of this country and I have learned many languages. There are some languages which I have forgotten. There was a time when I used to speak fluent Marathi because I had spent some part of my childhood in Maharashtra, Mumbai. I used to speak fluent Marathi. My mom used to speak fluent Marathi, but now I have forgotten it completely. Except, of course, some choicest words. I don't remember much of it. Why is that happen? Is that a short-term memory? But look at English, for example, or Hindi. That comes spontaneously. It's in my long-term memory. Second thing, long-term memory. One more example I'll tell you. I'm a born left-hander, but when I grew up with my grandparents, they insisted that I write with my right hand. So what happened is, see, look at the beauty of human brain. When I first practiced my first writing with my left, I can still do that. I still have that trait. Now I can write with both my hands. So what is responsible for that? Your temporal lobe. It's responsible for your long-term memory. Now look at the thing, like the other one on your frontal lobe. Like let's say, for example, I heard a song in 2015. Let's say some random song. What songs are famous in 2015? There would be some songs which would be famous in 2015. Let's say you have heard it time and again, you have heard it, but after that you have never heard that song. Would you remember it? Inch by inch lyrics, if you have not heard it after 2015 again? Like some songs get stuck irritatingly, that's a different story. Like because 2015 songs, one thing comes to my picture, that DJ Wale Babu. That song is so irritating that it is still stuck in my head. That's a different story. But there could be some song which you would never repeat afterwards, right? You'll forget it. So that's your short-term memory. Names mostly fall under short-term memory. people whom you don't meet much, you tend to forget your names. I forgot my manager's first name because I didn't see him for a long time. Ramesh sir, right? Yes. So that is your cerebrum. And parietal lobe is something which is responsible for most of your intuition, gut feeling, intuition, a lot of lot of involuntary decisions, or mostly the decisions related to your internal organs, how brain judges and how brain, like let's say you might have heard in your biology classes in your childhood, like the what do you say, fight and flight syndrome of adrenaline glands. So if adrenaline is released in your body, you have that fight or flight syndrome. How is that judged? It's judged using this parietal lobe. Now, why I'm explaining you all these things is because in neural networks in computer, in computing, they have derived this neural network equation based on different parts of the brain. So I have convolutional neural network, CNN, that I was telling about to you before we went for a break, which people use it extensively for image processing. CNN completely mimics the way how your optical lobe works. How do you process your pixels? What kind of data your brain processes? So when I see a color, why would I say that color is red, blue, or green? How do I say it? So your brain is processing all the pixels, pixel densities, and that is how it is coming up with a conclusion. That is how it is classifying them into a color. Or let's say a ball is coming towards you. Either you duck it or you catch it. How do you judge it? Your optical lobe judges it. It constantly calculates the distance and suddenly it judges like, yes, I have to put my hand and catch the ball, right? Or else, yes. So convolutional neural networks is one such application or one such mimic of your optical lobe. We have something called RNN, recursive or recurrent neural networks. Not recursive, I'm so sorry, it's called recurrent neural network. There is a separate thing called recursive, which is a different story altogether. So recurrent neural networks works on short-term memories. So short-term memories is something like, for example, a simple thing. If you're listening to this class, you have been listening to the classes since October. The data science classes have started from October 2nd onwards, 3rd onwards, right? You have been listening to a lot of classes. You had listened to let's say stats class. Then we had linear logistic regression and so on. There are some terms you clearly remember. What should be the y variable in linear regression? Normally distributed. How did you come up with this? So something got imprinted, like something got transferred into your long-term memory. But if I can ask you, what do you mean by recall? You can't recall. Hey, no. Yes. And what is specificity? 1 minus sensitivity, right? No. What do you understand by precision? True positives? True negatives? What is an elbow curve? What do you have on y-axis when you're drawing the graph for elbow? You can't remember all this, but when you were listening to the class, you understood it. 2 days after the class, you would still remember it, right? But when the new information got into picture, you forgot it. Or for example, let's say for example, I told you some wrong information while teaching you stats class. Let's say I said z-test can be used for any curves. Let's say that is a statement that I've said. Or let's say I said specificity is 1 minus sensitivity, for example. Some wrong information I have fed you. The very next day I come and correct it. I said, guys, I'm so sorry. Yesterday I said that z-test can only be used for normal curves. It can't be used. Z-test can be used for any curves. But no, I'm wrong. Z-test can only be used for normal curves. So I've corrected myself. So what happened immediately? So the information that was stored in your brain immediately got replaced with a new information, right? That is what is happening with you guys. At the moment, at the time when you were listening to linear regression classes, you were very well able to remember everything. Even if I had asked you questions on that day itself, you would remember it. Next day, you would still remember it. Third day, you'll still remember it. Fourth day, when Chandra sir would have started your logistic regression class, new information was kicking in. and eventually you forgot what was there in logistic, right? So that's your short-term memory. RNN is an implication of that short-term memory when your information is dynamic, right? Then comes something called long-term memory or artificial neural networks. That is what we are about to discuss today. So ideally, what should happen if I am teaching you linear regression from day 1 to day 4, from day 5 to day 7, I'm starting logistic regression. Ideally, should you forget linear regression? You should be able to remember everything, right? If I ask you the definition of R square, you should be able to tell it. If I ask you the definition for MSE, you should be able to tell it. And if I also ask you the definition of sensitivity, specificity, recall, precision, or maybe misclass error, concordance, discordance, everything you should be remembering, right? Elbow curves, and then comes ARIMA, or what do you say? Arimax. You should be able to remember everything, right? Yes. So that is what is facilitated using artificial neural networks, right? All right. Now, what is this ANN is all about? So let me tell you one interesting thing about the human brain. Just give me a second. Let me. Today is November 23rd, right? I'm using a system which will send me a Happy New Year 2016 on November 30th, 2018. That's that slow. Okay. The major motivation towards artificial neural networks is, this is actually a proven theory. I mean, like they did not test this on humans, but they had actually tested it on mouse, obviously, of all people. So if you can just look at this, I have my auditory cortex responsible for hearing, and I have my optical lobe, which is responsible for seeing. So let's say I disconnect my I disconnect my ears, and somehow I'll change the wiring and I'll connect my eyes to my auditory cortex. Yes, the funny thing about human brain is, or any brain, any system of nerves is, if I'm connecting my eyes to my auditory cortex, after a few days it will lose its optical ability, and using my eyes I can hear things. Sounds strange? How do you smell? What is your nasal cortex? Nose, right? How do you smell? It's through the nose, right? How do you think snakes smell? Using the tongue. Why? Because their wiring has been modified. We use our tongue to feel the taste. You have 5 different types of tastes that a tongue can feel. 5, yes. 5. Sir, Ugadi, sir, you have 5 different tastes, right? So in snake, some of the connections from tongue is linked to your nasal cortex. So that's why it will be able to smell through its nose. Sorry, tongue, yeah, smell through its tongue. So likewise, oh, hello. So likewise, you have this thing called, like, if you're disconnecting your ears and connecting eyes will start to learn. So this is how your human brain works. So what is happening is, you have a set of inputs, you have a set of layers which process it, and then you have a set of outputs, right? Inputs, processing, outputs. If the inputs are changing, if the type of inputs are changing, the inputs that you give to the processing chamber, if the types of inputs are changing, then the outputs will definitely vary. But still, some or the other processing would take place. Clear? This is the basis for your ANN. So neural networks is a term which is used for brains actually. It's a biological term. It's not a computing based term. We will never use neural networks as a part of computing based terms. So what happens in neurons, just pay attention a little bit. I have these parts which are known as dendrites, right? I have these called axons. Look at the way I'm drawing the arrow marks, right? Axons, dendrites, and let's call this as the body or brain or whatever. So in computing terms, dendrites, they take the inputs. And of course, needless to say, this is your output. Yes, this layer is your processing layer. This hidden layer does all the processing. Who does it? What type of processing it does it? At this point, it's a black box. You don't know. It's a hidden layer. That's why I use the term hidden layer, right? So this overall is known as nucleus. Nucleus, and nucleus is responsible for processing. And what does it process? It processes information which comes through dendrites and gives out the outputs through axon. Now, just after axon, you have another neuron attached to it. So dendrites of another neuron gets attached to the axons over here. So this thing is another neuron. So this is a dendrite of another neuron. So the outputs of axon are passed by the next available neutrons. So here also the processing would take place, right? It can be a similar processing like this or a different processing. I don't know at this moment. Again, it gives me some outputs through its axons, and it is again passed on to the dendrites of another neuron, and the step goes on. So part of the reason why we can multitask, right? Or part of the reason why we can retrieve information based on multiple things. Looking is one thing, how you can get your memory back. Now, let's say you forgot what is specificity. You look and read the definition, your brain will again recollect everything, right? What I did, how to remember definitions, especially like for instance, I had to remember a lot of stuff. Okay, logistic regression is one thing, but I have to remember a lot of stuff, let's say. So what I used to do is, I took a small, my mom had, like somebody gifted her like these perfumes and all. So those were the small bottles. I took one bottle randomly. Whenever I was reading this, I smelled it. I just put a small part of it on my hand and I was smelling it. So let's say if I had to read it again, I did this experiment multiple times. So this week I was learning linear regression, logistic regression, and I was smelling that perfume. I was like periodically I was smelling that perfume. After like let's say 1 month, if I'm revising it, again I did the same thing. Whenever I come across the terms, somehow I would get that bottle out of my desk and I just smell it, right? Eventually, let's say, anyways, I remember those terms now because I have taken a lot of classes of that. But still, let's say, eventually I had to recollect this entire thing after 10 years, let's say. That smell would definitely trigger these memories. You know that? Yes, smell would definitely trigger those memories back. Try it. I mean, like, let's say you visit a place which you have visited long back in childhood. Some visual things can make you recollect stuff what you have did there. But more than visual things, smells would get you a lot of memories back. Why is this happening? So there are multiple hidden layers which are working here. One layer of neurons. One layer of neurons was responsible for your visual memory. One layer is responsible for your smell. Both the things combined into one single hidden layer. So whatever input was given to you in form of vision and smell, you were able to give the outputs. Yes or no? So this is how it works. So this is how your neuron works. Feed the input, get the computation done, send the output, right? Now, let's see how ANN works. 1 second. Yes, this is how a neural network works. So as you can see, the circles that you're seeing here, these are a lot of my inputs. Every circle is my input. So if you're looking at it in terms of our business problems, let's say if I pick up our churners problem, or what did we discuss during logistic regression in the class? Which case study? Credit card what? Defaulters?
Yes.
Credit card defaulters. So let's say, or okay, let's not get into that. Let's get into a simple example first. Let's say XYZ person. Let's say I've got a new friend, Mr. N. Mr. N's friend is my mutual friend, let's say. Through him, I got introduced to this guy. Now, let's say this guy gave me one impression saying that N is a nice person because he's so and so. So that information went into my system. Yes. Now, let's say I caught N doing some unwanted activity, which left a very bad impression on me. So apart from the input, apart from the good input that I have got, I also now have one bad input getting in. After this, let's say some other person told me one more bad thing about this guy. Yes. So this bad things kept on piling, or maybe randomly I saw one good act of him. Now, all these things went into this processing unit. Yes. N1, N2, and N3. Yes. So after getting into the processing unit, what are the maximum lines over here out of the three classes? Let's call it as negative, positive, and neutral. What are more over here? Negative. So what do you think will be my output? The final output will be negative. Right? That is how it happens, right? You start to hate a person. I mean, like it's always difficult to love someone. It's always easy to hate someone. So that's why in logistic regression we take bad as one. That's easy. Churners are taken as one. That's easy. Agitators are taken as one. That's easy to consider. Just kidding. All right. So this is how it worked, right? So if I can just come back to our business problem here. Let's say I'm giving some green inputs. In my past data, I have observed that, let's say, a person from age group 30 to 35 is always a good customer. A person who is married is always a good customer. But let's say a person coming from let's say, for example, a person who is not having a own house is a defaulter. Or let's say a person who is not having a car is, let's say, a defaulter. For example, I'm just giving an example. So this was my age group, this was my marital status, this was my house. So let's say number of years in the address, number of years in the current address is less than 5. That also I'm putting in red. It's a defaulter. And let's say I have one more case where, for example, I have someone who is a female or a male, let's say gender. That fellow was a defaulter. Now, if I'm getting a new unseen data, which is falling under the same exact categories as my training data, what would be the machine classified? Finally, the machine will classify it as a defaulter, a delinquent, based on the previous inputs, the inputs which were processed over here, right? This is how your neural networks work. Clear? So I can have a single layered neural networks, as you can see here. Inputs, this is your inputs, this is your processing units, and this is your outputs. Just like how a neuron works, right? Yes or no? Now in computing terms, how can you imagine implementing this kind of a structure? You don't have circles and all in computers, right? What do you have in computer so that you can implement this? Matrices. Yes or no? So consider this to be like, let's say I have like 3 classes in x1. So I'll have x1 class 1, x2 class 2, x3 class 3. I have 4 classes in x variable x2. So I'll call it as x21, x22, x23, and so on. So basically matrices are being given as an input, right? Here in this layer, a matrix multiplication would have taken place. Yes. Finally, you have got your output class, because labeled data is also getting inputted here. You're getting a labeled data, which are these green and red lines on positive and negative. You're also getting the input matrices. Some matrix multiplication process will take place inside this processing unit, and then finally you have your output, which is also a final matrix, right? So if you have a y variable, good afternoon, you have a y variable that also gets classified as some or the other, like either delinquent, either event, or non-event, event, non-event, non-event, and so on, right? So you got your classification output. Clear with this? This is how your ANN works. Now, is the processing part as simple as matrix multiplication? Or yeah, it can be. It can be as simple as matrix multiplication. Fine. But is that the correct thing to do? Or do I have to use any particular calculations in the first place? And if I do, what kind of calculations do I use? So that is what we have to decide. So this is okay. One thing. This is your single layered network. Single layer network. I can also have a multi-layered network like this. Please look at this. I can have a multi-layered network. Inputs coming to an intermediary processing unit, again getting into one more processing unit, and finally I'm getting the outputs. And look at how I have connected them. So this one circle, let's call it as x1, connects to all the three n1s, processing units. So x1 to n1, x1 to n2, x1 to n3, x2 n1, x2 n2, x2 n3, x3 n1, x4 and n2, x4 and n3, and so on till all my x is solved. And what is x here? X is your feature variables, right? X is your input variables or feature variables. Clear? And not to be confused with the processing parts. Processing parts are not your final outputs. Processing parts are those places where some processing takes place. Your final output is denoted by the final layer, right? So you can have one layer, single layer between input and output. You can sometimes have multi-layers between input and output. Is that clear? Now, again, I'm saying when I talk about the process can be as easy as matrix multiplication, or it involves some mathematical formula, or it might not involve any mathematical formula. If it has a mathematical formula, what is it? What formula should I be using? That is what is our basis for neural networks, ANN. Is that clear? Let's look at it. Let's take an example where I have 7 inputs, x1 to x7. So let me write it down afresh. So x1, x2, x3, x4, x5, x6, and x7. So I'm putting this into multiple layers. Let's call it as n1, n2, and n3. 3 layers. And finally, I have my output layer n. Clear? So let's say there is a linear relationship between these two. I don't want to get into a simple matrix multiplication. Let's just see it in terms of what we know more frequently. So let's say there is a linear relationship between this one, x1 n1, x2 n2, and x3 n3. So these are my first line that I would be drawing, right? So how can I express this? How can I express this? I can say x1 is equals to beta 1 1 not n1, I'm sorry. Let's say n1 is equals to Okay, that's the half story. So x2 has links with n1, x2 would be linked to n2, x2 would also be linked with n3, x3 with n1, x3 with n2, and so on, right? The entire diagram continues like this, right? So I have n1 is equals to some beta 1 times x1 plus beta 1 2 times x2, where beta 1 exclusively belongs to n1, right? Plus beta 1 which exclusively belongs to n1, beta 1 2 belongs to x3, sorry, yeah, plus so on till beta 1 7 times x7. I can come up with this equation. Same goes with n2, same goes with n3. Yes, so what will change in n2? So beta 1 becomes beta 2. And likewise in m3, this becomes beta 3. 3 over here and 3 over here. Is that clear to all? Yes. So this is how my three equations work, isn't it? All of you? Is that understood? Yes. All right. Now, what goes with this final n? Now, this also should have an equation, ain't it? Now, your final n will be a product of n1, n2, and n3. Do you all agree on that? So how that would be? Let's say now instead of using beta, I'll use gamma n1 plus a gamma n2 plus a gamma n3. Right? Clear? Just go back here and see this. I used a term called weights for long-term memory. Right? This way, I mean, like in real human brain, this weight is something which is a kind of a factor for your neurons to be able to distinguish or to be able to keep it in long-term memory or short-term memory. It's the weights which decide everything. Right? See, there are some people who get addicted to some or the other kind of thing like smoking or drinking. But people who got addicted, there are high number of chances that they can come out of the addiction. Yes or no? So when they got addicted, the beta was very high. Beta 1 cigarette 1 was very high. Somehow, through the iterations, what happened? They realized that that is going to do a long harm. They have totally quit it. So your beta 1 related to this variable has got converted to 0, right? Which means this variable is no longer, yes, existing. Yes or no? So the weights that we begin with, these are not the final weights. These weights can change. And through various iterations, we can come up with this optimal beta 1, optimal beta 2, optimal beta 3. All the betas. How many betas are possible in this case here? So for here it is 7, 7 3 is 21. 21 plus 3? 21 plus 3? Guys, that is supposed to be in your long-term memory, right? 2 plus 2. What is 2 plus 2? 5, right? Yes? Good, good. So we have to estimate these 24 weights. So what I was saying is here, the way how you remember things depends on weights, right? Likewise, I'll not be using the word weights. I'll be using the word estimates. Sometimes you also find this factor called weights coming into picture. Clear with this? Now, that is the reason why how you can change things, right? So if you're assigning a weight, so let's say, for example, somebody said XYZ person is a bad person, but I saw him or her doing a very good task. So that might change the impression on that person, right? It is all because these betas are varying. Yes or no? See, whatever examples I said, they have a definitive meaning on ANN processes that I'm talking about. Is that clear to all of you? Right? And the smoking example is also one of such thing. Like, so the relative weight for not taking a cigarette is low initially when someone gets addicted. Eventually that weight can change, that beta can change. So the beta related to no smoking, if it increases, the person might quit smoking. Yes or no? That is how it works. So let's see, how do we estimate these betas? Now, before we get there, so betas and gammas are the weights. The equation here is the input function. So let me show you that slide. Here, apart from your x variables, you're also including your weights. See this? So that's the reason why I have used the notation beta 1 x1, sorry, beta 1 1 x1, or beta 3 2 x2, and so on. So w of j comma I, that's your weights. Here, look at this input function. This function can be any one of those functions. Like in this example, I have taken a linear equation. You can take a binomial logistic regression equation. You can take any other equation, right? That's your input function. Here you have an activation function, or I can consider this, I mean, like in simpler or layman's terms, I can consider this to be an optimization function or something like that, of something that sort. Yes, or a function which is deciding on how I can transform these weights and so on. And then finally comes my outputs. Clear? This is how it works. So this is what I've written over here. Now let's talk a bit about this activation function. So what kind of activation function does it exist? So activation function is nothing but something which can be used to optimize, or something which can be used to transform your data. So let's say you're beginning with a simple linear equation and you're building your neural network, which is how it is done actually, right? So I have now got two challenges. One, of course, like I have told you, estimating the weights. So I have got like 24 weights to begin with. I'll have to estimate these 24 weights. Next step is, let's see if this equation is valid for the data or not. That is my second challenge. Whatever data I'm using, is that really, I mean, like, whatever data I'm using and whatever equation I'm fixing to, is that equation really solving my problem? Is that equation really addressing my trouble? That I'm about to see it, right? So if the linear equation is not solving my issue, is not fitting well with my data, then I'll have to use an activation function. This activation function is nothing but a transformation function. So I have linear activation, where you'll be using the same linear equation which you have used before. You will not change your linear equation. There is logistic activation function, where f of x is equals to exponential of f of x by 1 plus exponential of f of x. There can be hyperbolic, and then there is something called threshold. Threshold is where you are fixing certain limits or endpoints beyond which you are not changing your betas. Clear? So these are some of the activation functions available. One such modern activation function that people keep talking about these days is ReLU. R-E-L-U, ReLU. I'm not getting to that because I don't have, of all the things, I don't have a processing power. Even if I'm using a 16K RAM, so I might not be able to run an end-to-end project and explain you ReLU. Plus, it's a relatively new concept. No one has an empirical proof that it can be applicable practically or not, right? So I'm just ignoring that. Other three are the ones which we are using for Python implementation purposes. Clear? Now this is strikingly similar to what we have discussed about kernels in SVM. There also we have to use a transformation function. Here also we have to use an activation function. Yes, the same concept over here. All of you, is it clear? Now, let's say the next one is estimates. So approximately not 10. In the above example, I have 24 betas in the above example. So we have approximately 24 weights in the above example. Clear? Now, how do we begin? I mean, like I said, you have built this neural network using these equations, all fine. Clear? But now I have my linear equations, but I don't have my betas, right? Where do I derive these betas from? I don't know, right? I'm not sure about where to begin with. So what I'll do is, initially, either randomly or based on some business explanations or exploratory analysis, or using any proper sampling technique. So what I'll do is, initially, we'll begin with some approximate weights. Initially, we'll begin with some approximate weights. All the 24 of them. Clear? I hope you're able to understand that. We will initially guess some weights. The algorithm will initially set some weights and it will start the process. Now, next up, second, we will use a learning function or a training rule. We will use a learning function or training rule. This rule will help us modify the weights. This rule will help us modify the weights. Is that clear to all? So here we go. This equation is written something like this. Right? Where R is your learning, rate of learning. Xi is of course your ith input, right? T is your target output. So let's say, for example, there is one set of class x1, x2, x4, x7. There are certain inputs to it. You know that this definitely will give me probability of, let's say, event is high. So you know that there are certain parameters x1, x2, x4 and x7 which will definitely give me my high probability to my event. That is, my classifier will be 1. My class will be 1. You know, the probability of 1 is high with some inputs. So you have this as your target input. And you also have something called actual output. A is equals to actual output. So T minus A, your target output minus your actual output. Target output is you're expecting something to be 1, or you're expecting a certain value, like let's say 200.7. But your actual output is something else. Let's say your actual output is 195, or your actual output is 300 or 230. Not what you are expecting, right? So look at the equation here, T minus A. Aren't you judging your accuracy here? Error, right? So that is also one part of the input, right? Your target output and your actual output. And then comes your R and Xi. So this is your entire equation. Wi is equals to R into T minus A Xi. I'll show you. So whatever I have explained, this equation, the exact form is this, right? Or maybe let me show you. I'm so sorry, not that. Yes, this is your exact rule. Clear? So this is your training rule for your single layer perception. So what do you feel like if your rate of learning, rate of learning is high, then what would happen? Very high. If your rate of learning is very high, the process would get stuck actually. It will not yield proper results. If your rate of learning is too high. If your rate of learning is too low, your process is slower. Not process is slow, your machine will not be able to learn it fast. Or even if it comes up with an output with a low learning rate, your output will have high error. You not have proper outputs. So learning rate should be an optimal level, not too high, not too low, right? So this can also be a part of your input. So whenever you're passing the rate of learning, just make sure you're not passing a too high value or a too low value. What will happen if your target output and actual output are same? No error. What will happen? Your weight will be equal to weight, right? It will not change. So let's say your estimation started with your beta is equals to 0.5. So if your both target and expected outputs are same, so your beta will remain as it is. It will not change. Yes. So this is the equation for learning, and the generic equation for your weights and your x variable is expressed like this. Is that clear? So you will begin with some inputs by adding some weights. You will sum it up because we had form a linear equation, right? So you will sum it up and finally you will have your outputs. So this is m1 x1 plus m2 x2 plus m3 x3 plus c. So there will also be a factor called c over here, right? Which we have not mentioned. There would be c1. There would be another coefficient c2. There would be c3. Here c4. So your total number of intercepts and coefficients become 28. This is what you have to estimate, right? And how will you start with? Like I have told you, you will begin with some default weights. Keep deciding one training rule, and based on that training rule, your weights will change. This is how the algorithm will work. And at the end, it will come up with final optimal number of beta equations. Some betas will get converted to 0. Some betas will remain as it is. Some betas might increase. Some betas will decrease. To find out the weights. Why do we find out the weights? Especially because we begin with an assumed weights, right? That is not my final model. Now, once we have these weights, our model is built. We can pass our inputs through it. We can rerun the equation with the new betas. Yes or no? So this is the entire concept behind ANN, right? So what would be your overall inputs? So throughout the function, what all would you take into consideration? First of all, your network structures like number of inputs and number of outputs, and number of layers that you are about to insert, number of processing layers that you wish to insert. Lesser the processing layers, less accurate might be your results. And if you're increasing the number of layers, your calculation time might increase. So you have to just do a trial and error and just come up with the optimal number of layers, a 2-layer or a 3-layer when you're going for a multi-layer solution. Is that clear, guys? Next level of input is what type of problem you're looking at. Are you looking at regression or are you looking at classification? So if you're looking at those, so based on that, you can go for your activation functions, right? Yes or no? Your activation functions can depend on those kind of inputs. Threshold. So let's say you're using a classification model on ANN. ANN always comes up with a probability score for classification. So what threshold are you setting? So if you're setting a threshold at 50%, for example, or 5%, or whatever it is, so if it is more than 5%, the probability, then it will be classified as an event. Or if it is more than 20% or more than 30%, it will be classified as an event. Or it will be a non-event. So I think we have discussed the same thing during logistic regression, right? Your GLM yields you probability score. You have one value called optimal cutoff value, right? So that is what is threshold over here. So should you go for a classification model, you can have this concept of threshold, right? Learning rate. So this is what I'm talking about. So is it 1%, 10%? So don't keep it too high, don't keep it too low, right? So by default, the learning rate is 0.01. By default, the threshold is 0.05. Is that clear? Lastly, your activation function. So whether you want linear, whether you want logistic, and so on. So activation function is also by default linear, right? Number of iterations to estimate betas. How many times do you have to repeat the process of training function to estimate betas? That's my last output, last input. Is that clear to all? Yes? Now, so just look at a small example on how we are calculating these betas. I mean, like a small mathematical example. So you see here, so what is my output? So what is my actual output? I already have my output, right? In my labeled data, I'll definitely have my output, right? So what is my actual output? 0. Y is equals to 0 is my output, right? Guys, what happened? Hungry? Sleepy? Y is equals to 0 is my output, isn't it? What are my inputs? X1, X2. So X1 is 0. I mean, like some input, let's say, for example, marital status. Let's say someone who is married, I'm calling it as 1. Someone who is unmarried, I'm calling it as 0. So X1 is unmarried. X2, let's say I have 4 categories, 1, 2, 3, and 4. One, two, three, and 4. So let's say I am saying X2 is equals to 1, category number 1. Now I'm setting a default weight. X1 is 0.95 and weight for X2 is 0.15. Now what is this over here? B. B is my processing layer, right? Yes or no? So here the weight for B, I'm deciding it to be 0.49. And I'm just assuming B is equals to -1. Let's see why, right? I hope I'm clear what I'm saying. So one random figure that I had did where I had these circles and all, where I was passing the input to 2 squares and getting the output. So instead of taking arbitrary values, I'm just taking some proper values over here, right? Yes or no? So in which I have 2 inputs. I have just 2 inputs, X1, X2, and I'm passing it to the processor function, which is giving me the output. Clear? Now look at this. Your output U is equals to minus 1 into 0.49, this one, plus 0 into 0.95. So let's say first, how do you get this equation here? We'll get like n1 is equals to beta 1 x1 and beta 2 x2, right? So how do I get it? 0.95 into 0 plus 0.15 into 1. So I got n1 is equals to 0.15. Now how do I get this final equation here? So gamma x plus c, right? Final equation will be gamma x plus c. So combine all the equation, I'll have this. So gamma is equals to x plus c is finally calculated like this, which is minus 0.34. So minus 0.34, let's say I'm setting my threshold at t. So this minus 0.34 is less than my threshold. I'll classify y as 0. Clear? So that is where I'm getting my output called y is equals to 0. Is that clear to all? So based on the calculations, I'm getting y is equals to 0. You can do a simple linear calculations like this, right? Yes or no? Which one? B is just an assumed value. So let's see, like beta 1. Beta 1 is 0.95 into 0 plus, so this entire value is 0. This is 0.15 into 1, right? So beta, I'm just assuming one value to be an input for my processing part n. Just an input. Kind of, you can say x3. Not x3, x3 should be coming from here. Let's say this is coming from some other input. It's one more, not layer, some more feature variable, some more input, some or the other input, right? Now, if y is 0, but I would say that my target output is 1. I wanted my target output to be 1 because I know with a set of parameters based on my intuition or based on my past data, I know that those set of parameters should give me 1, not 0, right? So I'll just compute my error. So error is equals to 1 minus 0, 1. So whatever correction factors or R, which is your learning rate, whatever you are using, so you come up with 0.05. So learning rate, just say I said like it is 0.01. You can also come up with a final error of or correction factor of 0.01. Whatever is your learning rate. Here I'm assuming my learning rate to be 0.05. So finally, what will be your new weights? So your new weights is original weight W plus R, or your learning rate, multiplied by error multiplied by X. Yes, right? So your W0 would be 0.49. Your weight 0. Okay, yeah, this is one of your X variable as well. Let's say, yeah. So 0.49 plus 0.5, which is your learning rate, into error into minus 1, which is your input. Yes, your weight is 0.44 now. Your W2 is 0.95 now, and W1 is 0.95 and W2 is 0.20, which has now changed, right? Right? Again, you'll go for an iteration process. Once you get into an iteration, let's say again my y is getting 0. Now I'll be using my new weights. Now I'll say 0.44 plus 0.05 multiplied by 1 minus 0 multiplied by again minus 1. I'll get my new weights. Again, I'll repeat this iteration. I'll repeat this iteration till I get my target output and actual output to be same. If both are coming once, which means my final error is 0, at that point my W will stop increasing, right? It will remain constant for that point onwards, right? So this is my number of iterations that I've told you for ANN. Is this clear to all? So where this was all began, it begins with number of inputs to a processing unit or a processing layer. then your outputs. I would call this processing layer as hidden layer because it can contain one layer or it can contain multiple layers. My entire exercise is to first come up with a line equation. Y is equals to mx plus beta x plus c form of a line equation. Yes, after coming up with that, I'll have to optimize my betas. Once I optimize my betas till my till I get a low error rate, my betas will become constant. Once my betas have become constant, I can now finally use that equation for my next steps. Clear? Now, which equation I have finalized in this stage? It's a linear equation. Now, let's say my linear equation is not fitting well with the data. Now, then in my next step, I'll change my linear equation using some activation function. I'll change my linear equation depending on what data I'm using. Is that clear? So this is how ANN works. So yes, your coefficients must be estimated. Your activation function must be decided upon. After deciding on those two things, the other factors, let's say to change coefficients, I would be needing my learning rate. Yes, I would need my threshold. These are also some of the inputs that I will be passing through. Yes, by default, the code will set your threshold at 0.05 and learning rate at 0.01. You know that threshold has to be changed. So like how we decided optimal cutoff in logistic regression, we have to change this threshold depending on what data we are using. Yes or no? Like there can be some functions which can directly calculate this optimal cutoff value, or you will be deciding this optimal cutoff value based on how your ROC curve is working. There are a lot of other factors, right? So here also in this case, you will change your threshold value depending on some basis or the other, right? Learning rate by default is 0.01. In this example, I had taken learning rate to be 0.05. That can vary. It has to be same. You can't change those things. No. She's asking in the iterations, will this change? No, this will not change. This will not change. Pardon? Bias needs to be added. I mean, like, again, it depends. It depends. We usually avoid adding any kind of bias. We should be avoiding bias, right? Because again, underfitting. So it depends, I would say, right? 1 second. Now, I have two ways of estimating betas, two kinds of iterations. That is, one iteration, what we have seen is a forward propagation, left to right. The other can be a backward propagation. So this is also last input that you can pass. What kind of iteration do you need? So number of iterations and what kind of iterations would you proceed with? So this is your propagation, or you can have backward propagation. There are two methods to pass, right? So the example that I had taken here, this contains one processing unit and multiple 3x units and one output, right? So I've given one more example which contains a layer over here, three inputs, a middle layer, and your final output. You can also just go through this example, how the calculations have taken place, right? So this is exactly equivalent to this equation. Again, the difference between the one in the PPT and over here is like there in the PPT, I have only 3x. Here I've taken an example of 7x, right? Now, let's stop the discussion over here for ANN. Let's quickly get into your project discussion, right? You want to take a 5 minutes break? Yeah, just take a 5 minutes break. You can get into the projects discussion. So it's 12:05 now. I request everyone to be here by 12:10. Right? Just 5 minutes. Don't go out. 5 more minutes. Right? A little bit about your projects that you have to do and submit. Hardest part after all the fun. Yeah. Okay. So I hope by now you would have completed your basic Python exercises. Yes. No. Basic Python case study, 10 questions. Have you completed it? Did you complete your SQL case studies? Because whomever I was asking, like, what are you doing these days? Everyone is like, we're doing SQL case studies, sir. Especially, okay, these bunch of people are absent today. So every time I ask them, they're doing SQL case studies. All of you. Have you done SQL case studies now? No? Yes? Good. So you have this basic Python case study of 10 questions. At least you have gone through those questions, right? No. Opened it? No? Pardon? What is it? Okay. All right. So this you have 10 questions, 10 simple questions that deals with normal if conditions, lists, dictionaries. There will be one question on regex and one question on classes. Basic question. A little bit extension of that is your 100-question case study. See, not too difficult. So the 10 question that I've given you is on a slightly higher level. The remaining ones, they are just simple questions, like the ones which you can answer in one single line. That's why you have 100 questions. Like maybe I'll have a question as silly as print, which uses a simple print statement, or maybe like creating a list and extracting third element out of it. Those kind of questions. I promise. That's why 100 questions, right? Pandas exercises. I have again like 10 short and sweet exercises. Not 10. Yeah, 10 short and sweet exercises. So this covers everything related to pandas basic data manipulation. So you will have functions like simple creating your data using dictionaries, or maybe importing a data, or fetching the columns, or maybe like subsetting, sorting. Again, so each of these exercises will have like 5 or 6 to maximum 11 or maybe like 12 questions. That's it. Maximum. So on an average of 10 questions per exercise. Clear? Now all these 10 questions again can be answered using one single line. There is no doubt in it. There is no change in it. I hope that's clear to all. Yes? Now, just one thing. I think I have uploaded all this before as well, but just for your reference, I'm sharing this again. Now, regarding this pandas basic exercises, just remember, I mean, like I've told you, I have like 10 different exercises. Just be advised, don't use these files. If you have already started doing it, well and good. I'm giving you a slightly, I'll today in your LMS, I'll be adding one slightly modified form of this pandas exercises. I mean, like the one which I have shared has had some doubts in the questions and all. I have not changed any questions. I've just changed few sentences in the question, like just to make it more readable. Your answers will be the same. The questions I have made it a little bit more simpler to understand. Right? So I'll share that by today. If not, if you have started already working on these exercises, well and good. There is no change in what I'm about to share you and what I have already shared you. Clear? So you can start doing these exercises. Now, next up, so next up is Pandas case study 1 on data manipulation. Now, this tries to cover an end-to-end case study. Like in the exercises, all the questions would be scattered. Questions as in all the processes that you do in the questions would be scattered. Here, in case study 1 and 2, the questions will be more related to one particular data set. If I'm giving you a data set, what kind of data manipulations you should be doing? So that will be in case study 1, right? Case study 2, on the other hand, now the only difference between 1 and 2 would be joins. Case study 2 would contain joins. That's it. Nothing much. And I have data visualization case study. So the exact kind of things what we have done in the class on how to get bar charts, how to get pie charts and all that. So that will be there in this visualization case study. Try attempting that as well. Now, basic statistics case study 1 contains 5 different data sets and 5 different questions. So you will be deciding like what kind of test you would be using. One sample, 2 sample, independent sample, or ANOVA, chi-square, correlation. So what you're about to use, you have to decide on this. This case study is exactly similar to the case study that we have discussed in the class. Remember the credit card campaign case study? Is the campaign successful? Is there any relationship between male and female? Or is there any relationship between the segments? Or is there any relationship between segment and region? Or segment and credit card spend? So all these things. This is similar to that. So is case study 2. Case study 2 is based on one single data, on user perception, right? A combination of these two would be there in healthcare case study. It will be an end-to-end case study which contains data manipulation and basic stats. Is that clear? You should be, once you have done all these case studies, that should give you enough practice to finish up healthcare case study. Clear? Now, these are your basic case studies, and I'm expecting it to be finished up ASAP. Then comes your projects, your final projects. I've got 2 on classification, 1 on segmentation, 1 regression, the other forecasting. Right? These are the 5 case studies that you must submit, apart from your previous ones, of course. These are the 5 case studies that you must submit as a part of your certification, right? So I will not get into the details of it because you are the one who has to decide on various factors, but I will definitely give you a gist of it. So for example, if I pick up my linear regression case study, just give me a moment. So in my spend prediction problem, that's obviously a linear regression problem where I have a lot of factors where people are spending the credit cards in, and I have a variable which denotes spend. So I have various factors like their marital status, their like let's say, do they have their own vehicle or not? Do they have their own house or not? Right? Are they paying utility bills or not? Do they own pets or not? So there are a lot of categories like that. And finally, I have a spend variable. What is that spend variable and all? That you have to decide based on the data, right? So I need to find what kind of factors that lead to my spend, I'll have to come up with that equation, y is equals to m1 y is equals to mx plus c, and then finally I should predict it. Clear? So what you're supposed to do, one, first of all, just be advised that this data set has a lot of variables. This data set is having a lot of variables. First things first. So your entire effort should be in reducing the number of variables. So I would begin this reduction with a simple, like first let's say like my y variable is anyways a continuous variable, right? So how would I remove x variables if they are also continuous? Pardon? Correlations. Yes, I would have to look for correlations. So in my correlation matrix, if y and x are linearly correlated, then I'll consider them, else I'll reject them, right? That's my first method of looking at. Now what if x is categorical, y is continuous, x is categorical? What test should I do? Analysis of variance. So based on ANOVA, I'll have my significance value, and based on the significance value, if it is highly significant, you will consider that variable, else you will not consider it. Third, between x and x, again from the correlation matrix, what should be the correlation between x variables? High or low? The correlations between x should be low. If correlations between x is high, that leads us to a multicollinearity problem. Now, if let's say there are like 7 x variables which are having high correlation between each other, what would you do? You would consider one among those 7. That's it. Drop the remaining. How would you drop? Which one would you keep? Which one would you drop among all? Let's say out of x1 to x7, I've decided to keep 2. Which 2 should I keep and which 5 should I drop? What is one basis of seeing it? Correlation between, see, anyways, x1 to x7, these 7 x variables, I have found out that they have high correlation. I can remove every one and keep only 1 or 2. Let's say I'm deciding to keep 2 out of 7 variables and I want to drop 5. Which 2 should I keep? Or which one should I keep? Why are you going till VF? First of all, I'll keep that one variable which is highly correlated with y. That is my first basis. Why going to VIF at this phase? Not required. Hold your breath. So that is okay. Should you use VIF here? I don't know. Is VIF the correct process to use? I don't know. Right? But this is one basic information that I can reveal you at this moment. Right? So yes, if there is a multicollinearity, keep that x which is highly correlated with y. You can drop others. Or like in real terms, how do we do? We'll keep that one which we know that it is relevant for the business. That's why instead of saying 1, I said 2. Maybe 2 out of 7 would be in such a way that 1 is highly correlated with y. 1 might be less correlated, but maybe it's a little bit important for my business. Clear? Now, that being said, let's say there are multiple categorical variables that I have selected after ANOVA. After performing, first of all, I removed all those x which are not having correlations with y. Fantastic. Then I did all those x which are categorical and I performed ANOVA. What should be my next step to further reduce variables? Now here I can do 2 things. I can go for a principal component analysis, variable reduction technique. Yes. Factor analysis can also be done here. PCA, FA. You can employ any of the variable reduction techniques. Agreed? Or any other thing that you can come up with to further reduce variables before you build your GLM. Oh, sorry, before you build your LM function, is there any other method to gauge which variables would be correct? Stepwise regression, anyone? Yeah, p-value is all fine, but I guess you might have done stepwise regression as well, right? Yes or no? Pardon? Weights and all, yes. So VIF is one thing, yes. Stepwise regression is another process. Have you guys done stepwise or not? We have done, right? So stepwise, what is stepwise? So the one which gives you AIC, which AIC, maximum or minimum AIC? AIC should be high or low? Which is the best model? The one with high AIC or low AIC? I don't know. Debate among yourselves. Anyways, at the end of the day, you have to do your stepwise regression and decide on that model which gives you a better model. Yes? Guys, you have forgotten everything. No issues. Go through the classes. Everything will come back to you. Right? But yes, somehow your variable reduction is done. Now you will build your model. Next comes all the entire and elaborate process where you check or you validate your model after predicting it. Right? Sounds easy? Yes? It will be easy. Don't worry about it. We have already done one case in the classroom, right? So this will not be a big deal. Clear, all of you? Right? I am really confident that you will be able to do it by just follow all the steps how we have solved the case study in the class. Right? I hope you would do that for me, right? This has around 132 variables. Close to. So that's why I was a little bit emphasizing on the variable reduction techniques. Right? So figure it out. You can do that, guys. Next up, oh, why you guys suddenly started appearing depressed? Pardon? Hungry? कौन बोला yes? Yeah, I'm also feeling hungry. We'll go. Half an hour more, we'll go. Right? All right, guys. Guys, listen up for the NGO fundraising attrition. So basically, this has a couple of variables, and the Y variable is deciding whether a particular donator, a particular donor is still associated with the NGO or not. That's a 1 and 0. Right? So a lot of factors involved here. Now, small thing with this case study is I have given SAS7 BDAT files. You can see this? SAS7 BDAT files. I hope you know how to read a SAS7 BDAT file. You have to do nothing, just say read underscore SAS7 BDAT file name, that's it. But problem is, all these things should be concatenated or should be merged in a proper manner. That you have to decide how to do it. Right? So joins, appending, like pd.concat, pd.merge, I don't know at this moment. You can merge every table or you can concatenate every table. I don't know. I don't know how the data looks like because I don't know how to read this data. You know how to read this data using read underscore SAS7 read underscore SAS, right? Yes or no? So this will be one challenging task. Then after that, this doesn't have a variable problem as before, but still you have to do your own checks, right? Here, what is your Y variable? Categorical or continuous? Categorical. So can I use linear regression here? Obviously not. I'll have to go for logit, generalized linear model. Yes. So what precautions should I take? Does it look at dependency and correlations of X and Y and also? No, right? It doesn't. Pardon? Yeah, probability, that's my final thing, but initially, like we checked for linear regression, we don't have to do that here, right? Now, how do I decide what are my important factors? Maybe I might depend on ANOVA, Y versus categorical X, right? ANOVA, sorry, Y versus continuous X, I can go for ANOVA. Y versus categorical X, I can go for a chi-square. Yes, I can decide on few important variables as such. Instead of taking, like, if I have 30 or 40 or 50 variables, instead of taking all, I can fetch few significant variables by running of initial ANOVA and chi-squares. Yes or no? Then I'll build my models and then I'll be validating it. You know all the validation phases, right? Concordance, first of all, confusion matrix, concordance, discordance, and tight pairs. Then comes ROC curve, area under the ROC curve, misclassification error, sensitivity, specificity, and recall, precision. Yes. What else? Gini, yeah, so much D. So much D. And do we have MAPE here? No. We have misclassification error here. Yeah, area under ROC curve. Yeah, that's fine. ROC curve is mandatory. Yes. So optimal cutoff value decides your predictor, right? Before you even do predict, you have to decide on your optimal cutoff value. Now, optimal cutoff value, it's not just trial and error. You know how to get to your optimal cutoff value, right? So just go through the class recording when we discuss the case study. So if you fix it as a 50%, it can be good to some extent. Like by default, it is taken as 51%. See and run your data with 51% and keep increasing it. What's the main criteria to decide this optimal cutoff value? Yes. Or what do you say? Concordance should be high. There are other factors which you can decide on it, right? So my precision should be high. What are positives should be treated, should be classified as positives. My precision should be high. My events should be classified as events. Clear? And misclassification error should be low. That is how I'll decide my cutoff. So there can be some functions which can come up with an optimal cutoff value, or you can do your own hit and try. Clear? So that is how you will be working on this case study here. I have one more case study on classification. Just a moment. That is the telecom segment, telecom case study. Now, credit card spend prediction was linear regression. NGO fundraising attrition is classification. Now, credit card case study. I have credit card customers, just like how you had telecom customers. Yes, you'll be performing a segmentation over here. Is that clear? Easy, not much difficult. Same things, whatever you had did for telecom segmentation in the class, this credit card segmentation uses the same kind of methodologies. So you will begin with n number of clusters initially, and then keep increasing your number of clusters, and then finally come up with optimal number of clusters, right? Or best cluster solution. Now, one mandatory thing about this case study submission for yours is, first of all, we have given you a profiling sample, right, for telecom case study, for both variable reduction and your final output. What's so funny? So we have given both the profiling sheet for variable reduction and this one. What do you say? The segmentation profiles. Yes or no? Go through the files. You will get it. I want the similar kind of profiling sheets for these two projects, these two segmentation projects. So if you're coming up with a 5 cluster solution, briefly explain me why did you come up with that 5 cluster solution? How it was different from your 3, 4, and 6 or 7 cluster solutions? Why did you decide on your 5 cluster solution? And in the next sheet, what are these clusters signifying? What do you understand by cluster 1? Like how we did for telecom case study. I said cluster 3 is that cluster which contains mostly retired people, and they opt for voice or value added services, voice services and value added services. Whereas cluster number 1 consists of age group less than 25, and they are mostly interested in internet packs. So they have wireless device. All these components had been included in this, right? Those values were high in these clusters. So that's why cluster number 1 is young people. Cluster number 2 might be those people who are using international calls. Cluster number 3 are those people who are retired and they mostly use value added services and voice services. Cluster number 4 is exclusively for value added services. And cluster number 5 is a mix of value added and internet. So that is how we described, right? Remember? So in your profiling sheet, in your second sheet, you have to define this kind of a profile. What is your 5 clusters saying in your credit card case study, credit card segmentation case study, right? Understood? Next is telecom case study. Segmentation problem, you have to do 2 problems over here. One, in telecom case study, you have a segmentation problem. You have to divide and classify your data. And also there is a classification problem involved in it. Once you open the data, you will understand what I'm talking about. Clear? Yes or no? So these 2 things you have to do. And when I say segmentation case study, again, you have to submit your profiling sheet. Without your profiling sheet, this will not be evaluated. Because anyone can come up with your K clusters, but I have to have a proper explanation. Why 5 clusters? Why not 4? Why not 3? And why not 6? And if you're coming up with 5 clusters, in your next sheet, just describe what are these 5 clusters saying. What is cluster 1? What kind of observations do you have in cluster 1? What kind of observations do you have in cluster 2? And so on. That descriptions are mandatory. I hope you understand this, what I'm saying. Now, this telecom case study also has a classification problem to it. Look at the data and figure out what will be your Y variable. What classification are we doing on this telecom data? Clear? And of course, needless to say, I have a forecasting problem here with Walmart store prediction. It will be a time series problem, easy one, trust me. Go through the data, you will understand it. I'll not give further details because I want you guys to do the thinking part. Right? So till now, whatever fundamentals I have given, I have either given you instructions or I have given you the basic points, what you usually follow in any project. Right? Now, what I want you to do is just carefully look at how Chandra had solved those case studies in the class. Right? Do the same thing step by step. So fine tuning can also be done in these cases. So let's say, for example, outlier removal. Let's say you're fixing at 99% as we shown in the class. Now you can modify that depending on the data. You can change it to 95.5 or 99.1 or IQR or mean plus or minus 3 standard deviation. So that is how you can little bit fine tune your model. Or let's say if I'm doing a logistic regression case study and I have a class bias, my number of events and number of non-events are totally different. I have many number of events than non-events. So there will be a bias towards events. So I'll have to use some or the other undersampling or oversampling techniques to get my data to be normal. So these fine tunings you can apply so that it improves your accuracy. Is that clear to all? Right? Now, last but not the least, coming to your preparations, I think the interview material has been shared with you, right? The interview preparation guide would have been shared with you, guesstimates, puzzles, those things have been shared with you. And most important, you would also have now got some sample resumes, right? Didn't you? Yes, check it. There will be sample resumes. Yes or no? You're not checking the LMS. What happened? What? No, I'm talking about sample resumes. Sample resumes has been shared or not? Yes, no. Check it. So half of you are not even checking your LMSs. Nice. And now your primary task would be, yes, of course, solving this problem. There is no doubt about it. But start building your resume. Look at the way how they have built those resumes and start building your resume. And in your resume, these sections are good to have. And this is what I advise people to follow very generically. Just look at this. Your section number 1 in your resume would be summary. What are you doing now? What did you do in the past and what are you doing now? So you can say like graduate with 3 months of internship with so and so. Yes, and trained in analytics techniques. So that would be a good opening line. What are you doing and what are you trained in? So say like then you can add expert in so and so technologies, right? Or like don't use the word expert, have worked on academic projects related to analytics techniques, namely regression, classification, and so on. You can add it, right? And finally, in your end line, just put core competencies as whatever languages do you know, like put Python. Core competencies will be Python. Let's say somebody who knows R, they'll put R. Somebody who knows SAS, they'll put SAS, and so on. So you have put your Python, let's say MS Excel, Tableau, right? And yeah, SQL, of course, and so on. Right? So this should be a good summary. Don't write that I'm seeking for roles in data science industries. No, don't do that. You don't have a career objective because most of you are freshmen, right? So you will not have any career summary. Don't put career objective at all. That is so 1960s, right? So put up your summary, because when the guy sees your resume, he'll not say what you wanted to do. Just he or she is interested in what you're doing now, what you're up to. So somebody gives you a good gist. Maybe if you simply wanted to convey your feelings, put it in the next line. What is your objective? What do you want to do? Right? So I want to be a galactic superstar, president because of will. Put it there. Don't put it that way. Put it in a very humble and modest way. I don't know who trained one of my friends. Like we were having a campus interview on Infosys. As usual, they asked those cliched questions like, "How do you see yourself in 5 years?" So that guy actually said, "I'll be replacing you after 5 years." He forgot to say the next part of the sentence. That's like, I'll be replacing you after 5 years, and you will be in some other higher position. So egoism plus buttering both done on same hand, right? So Just take care of those things, right? Like this, don't do anything stupid, right? Clear? All right. So that's your summary. Second step, like if you can add career objective, that's fine. That's okay. Just leave it. Second is skills and tools. Here I want a proper table. One side you will have your tools like languages known, what are the stats techniques that you know, what are the tools that you work with, right? Stats techniques, tools, or what are the like for example stats techniques involved. Let's say for example your regression, classification, or time series, segmentation. Your tools should involve, your languages here are, let's say Python. If you have studied in your college C, C++, just add it over here, no issues. If you have not, just ignore this section, just put Python and leave it. Safety reasons, put R as well, right? Tools, on the other hand, don't write Jupyter Notebook, Anaconda, not required. Your tools should be MS Excel, Tableau. Oh, of course. How did I forget? This is one thing which every one of you guys are obsessed with, right? Tableau. Let's say, I mean, like if you're working on R, no, don't write R Studio and all these things. Like leave it. Like tools, MS Excel, Tableau. That's more than enough, right? So you don't have to say that you have used certain GUIs. I mean, like that doesn't make any sense, right? These two, however, they make sense here. Clear? If you have researched any other tool apart from these two, please mention it. ClickView, some people would do that. So just put ClickView if you have explored through it. Else leave it as it is. If you are really confident that you can work on any DBMS, or especially people who are putting SQL and people who are coming from computer science background and IT or MCA, just put whatever is the database of your choice. Don't put MySQL, just put Oracle or MS SQL, or sometimes both, if you're confident in both, right? Next up, so this should be in a proper tabular manner. It should be a proper table. I should be able to see a proper table over here. Third one comes your qualifications. Yes, education qualifications, I guess. No. 1 second. Yes, education qualifications, yes. Right? So mention it. Freshers, you're mostly supposed to mention your percentages, your scores, GPAs and all that. If any one of you have got any experience, you don't have to mention those things, right? I don't even remember my 10th percentage, so fine. And that is also not too big to remember, so forgotten. So all freshers should put up their 10 scores, 11 scores, and the degree scores. Next up is your experience. Now here is where you have to diverge. If you really have an experience, put as an experience. And if you're putting as an experience, just say like which organization you worked with. You worked from when to when. Let's say it has a proper end date. Like let's say company 1 is my most recent company. So I'll start I'll put my start date, right? And I'll just leave it as it is. I'll not put a hyphen and leave it. See, incomplete stuff is something which is not so attractive. Just leave it as it is. 2016 means the person is still working in this company. Now, what do we describe here? We will describe everything that would cover these things. Describe it in such a manner that can cover or justify tools used or skills that you have. So describe it in such a manner that it will justify the tools that you have used or skills that you have. Clear? That is mandatory. Please do that. Now, next up, let's say for example, here, what else should you put in the description? So what not to put? What not to put here is classified information, if any. So let's say you're working with the company, you should not be revealing any kind of confidential information like project or client name, etc. It's a big no-no, right? You can also mention which domain have you worked with. Let's say you have a programming experience and you built a software. Just write it down that you have built a tool for, let's say, you have built a tool to be used inside a academic or in a school, which will do so and so things. That's it. Now then describe like what you have done, which technology have you used. So what to put. So which domain the project belongs to. Next is like what tools you used here. What's your efforts in this? What's your role? What did you do and achieve? Yeah, that's one of the points. And finally, like if there is any cost savings, or if there is any cost savings or earnings or profits, you can include that over here. Because if you are on a little bit higher level, you will definitely come to know about these cost savings and all that. So, right? So you have to mention that. Now, that being said, so company 1 should be your most recent company. Company 2 should be your a little bit older one, if you have worked for multiple companies. So here we'll be mentioning like 2010 to 2016. That's it. Simply mention the years. You don't have to mention months and all. By that, you can hide few things. Right? If there is a gap and all that, you can just hide it out. No issues. So that's how you write your experience. Now, like I said, this is for someone who is actually having an experience. Now, let's say you are a complete fresher and you don't have any experience. Here is where you have to mention academic projects or projects experience. Project experience. So this is the experience that you have to mention as a part of your project that you have done. So you can include your college projects. There is no harm in it. And you'll have to include at least 2 among the projects that you have done here. At least 2 projects that you have done here should be included in this section. So take up 2 projects among all the projects that I have given. See the one which you have done it very well. Put it over here. And when you're putting it, again, no doubt my first point is justify the tools that you have used. What not to put is, don't write it as this is a linear regression project. No, don't put it like this. No one is interested. Just put that you have worked on a project which deals with predicting or which deals with determining the factors leading to card spend. Just like how we describe the project here, right? So don't put it as linear regression. That let that be a suspense till the last point. So just describe what you have done. Like let's say I have employed so variable reduction technique. Then I have found out that these are the anomalies in the data, and this is how I rectified. And then I have built the model and predicted it. And these are the ways how I have improved the model. And finally, I have used linear model or linear regression for this process. Simple and sweet. All right. Now, what to put now here? This is what I've explained, what to put, right? So brief description. What are the techniques that you have used? Let's say you have used let's say ANOVA, or you might have used chi-square, or you might have used PCA or FA, and of course LM, right? And then let's say what are the challenges faced and how you overcame it, right? What's your conclusion? Not conclusion, how you overcame it, and finally just say like what did we do? What did we do? Which means linear regression. I also solved this case study using, let's say for example, KNN. Also you might have used SVM for this, mention that as well, right? So finally, so this is what you can, how you can close it with. You can apply multiple techniques and solve. Oh, of course, I'm so sorry, I've forgotten to tell you, and please take this as one of the instructions for your project. Apart from your traditional statistics, you should also be doing the same run using your machine learning algorithms. DT, naive Bayes for your classifications, DT for both classification and this, ensemble learning for both for classifications and regression. Everything you should be running. Please remember that, right? I hope you would do that. And finally, if you can just put a final table in the end in Jupyter Notebook. Method followed by its accuracy. You'll have some error score, right? Or accuracy score, right? So how much accuracy did you get from LM? How much accuracy did you get from what do you say, SVM? How much accuracy did you get from KNN? Everything must be mentioned clearly, if you can, in the end of your project. Pardon?
Last one. The healthcare.
Which one? No, all your final projects. These ones, all the projects. All these projects must be done in traditional stats as well as machine learning. So see, there is nothing difficult in this. Still your data cleaning, everything is cool. That is where your effort goes in. Once you get your regression model running properly, then there is no other way to stop you, right? There is no stopping you. Once your traditional stats is running, it's all about using a small function as an algorithm. Like you have seen how did you do logistic regression. You have seen how the same logistic regression was a little bit more easier in DT. And you have seen logistic regression in naive Bayes. Like when we used naive Bayes in text mining, 1 and 0 got classified, right? So did I clean my data? Did I remove my outliers and anything? It's all clean up, right? Everything is clean, so you can just pass it on. The clean data, whatever you have, you can just put it. So your routes will diverge from that point when you're creating testing and training. So it can be your traditional LM, GLM, or any of these machine learning techniques. It has to be done here. Clear? And that is also what you're mentioning in your project experience. And don't write it as project one. Yeah, put it as project one. Put the title, like whatever title we have given you, like credit card spend regression and so on. Right? Now, once this experience section is handled, of course, you'll get into like any personal information, like for example, language is known, right? But having multiple languages, it's better for you. I mean, like these recruiters will think that like yes, you can target for various locations. All right, so that can be done. That could be a section, or you can add other things like hobbies and other stuff. They'll be more interested to know. I mean, like it's not just the what is academics part. You'll also be a little bit more interested to know you personally as well, right? And now, after you have finished doing this, make like 2 or 3 sets of resume, especially for your addresses. If your intention is to target Bangalore, very good. Put your Bangalore address wherever you're staying. If your intention is to apply anywhere, have multiple addresses. Like put a random address, no one is going to verify, right? So have an address in Delhi, one in Bangalore, and let's say you are applying for a company which is looking for a person in Delhi. Submit your Delhi resume. If you really intend to relocate, that is much easier. I mean, like it widens up your opportunity. That's it. So if you're sending a job to Delhi and your address is Bangalore, that creates a confusion. So they might think that you're not ready to relocate. But this is one mistake which actually I did when I was a fresher. So out of habit, I had put my house address in Visakhapatnam. So see, that gives a kind of a feeling like whether you are ready to relocate or not, right? So I got calls only after changing that to one of my Bangalore addresses. I changed it to my cousin's house in Bangalore, so I started getting calls. I got my job in Delhi. So that's how it works. So have multiple resumes, multiple addresses. That's the first thing you're going to do. But second and most important thing for having multiple resumes, you'll have to tweak it according to the job requirement. You can't keep sending blunt same resume for every job opportunity that you are getting. Let's say the job opportunities asks you clearly to have good knowledge on basic Python and MS Excel and Tableau, for example. So here is where you can make a change. In your project section, let's say you have applied, if you have put 2 projects, both on Python, add a third project over there, which says something about whatever you have done in Excel and SQL. That will add more value. Or maybe put it in the front, like instead of project 1 having linear regression, put project 1 as your Excel case study. If the job role is for Excel, Tableau and basic Python. Clear? I hope you're able to understand what I'm saying, right? Right? So this is one tweak which you have to do intuitively. No one would handhold and push you. No one will spoon feed you on this. You'll have to be intuitive and change it, right? Now, having said all these, we will be having a follow-up class most closely just before Christmas. So anyways, that will be confirmed to you. So if it's not possible, yeah, most probably on Monday, 24th of December, we might have a follow-up class. 24th, or it can be 26th, because 25th is a holiday. So either it is on 24th or on 26th of December. You will be having your follow-up class. Clear? But in any of the case, it will be informed to you via email. Please keep checking your email. Now that being said, this follow-up class will be useful if you have done something in this 1 month course, right? So this follow-up class will not be a kind of a teaching class. It will be a doubt clearing class, right? Plus we will see those cases of SVM and ANN, what we couldn't see. So let's say one follow-up class isn't sufficient. We might have 2. So last boot camp we had actually 3 follow-up classes, because yes, those guys, unlike you people, don't feel bad. Those guys were very regular, at least in completion of their projects. So that is one thing which I am yet to see in you guys. Maybe like take your time. I'm not criticizing you on this. Take your time, take your sweet time and do it. But Be regular. That's my earnest advice. That's it. Don't take it in another way. So those people had enough doubts that we had to have couple of classes more. So one classes for remaining topics, two classes for entire doubt clearing session. And I really appreciated what they had done. So I am also expecting similar kind of effort from you guys, right? So do that. And once you are finishing up your projects, then it makes sense to send your resumes for referrals. It will not make sense unless you know something, right? So within this month, if you are planning to apply for any jobs and all, just do it very light. Don't apply it for bigger companies as of now. Don't apply for any walk-ins to any bigger companies or any named companies for now, because you're not prepared. That's why I'm not encouraging you to do it. Startups, yes, you can apply, or job roles which deal with Excel reporting, Tableau reporting. Do that, because by now you are expert in those fields, right? So that is where you can target. Don't go beyond that, please, for now. Once you're confident enough in all these techniques, once you have done a project on your own end to end, then you may start applying on your own, right? Or maybe like once you get the certificate from us, we'll start referring you, right? Now, one caution about referrals: you have to clear those interviews, right? So maximum of 3 or 4 referrals would be given, not more than that. So if you're not performing well in those interviews, we will stop giving you referrals. So please be very careful about it, right? So before even we give you the referrals, we will have mock interviews and all. So if we feel that yes, you're doing well in those mock interviews, yes, we can go ahead with the referrals. But for mock interviews, you will be needing the certificate, right? So once you have the certificate, which means you have done your projects properly, you would be confident enough to appear for any interviews, right? Let's do that. All right. And good luck with your projects.